Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Let the gentle current of our words carry you as we drift through the vast, quiet expanse of human curiosity and the universe's own whispered secrets. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. Why do we, as fleeting beings, yearn so deeply to leave a lasting mark upon the canvas of time? What drives this quiet, persistent desire to be remembered to echo beyond our own brief moments? And what happens when that yearning, though beautiful, sometimes leads us down paths where the truth might be overshadowed by our own deepest wishes? But don't worry, we'll take it slow. This isn't a race through equations or a dash through historical dates. It's more like floating through a galaxy of ideas with a cup of chamomile tea, allowing the gentle light of discovery to wash over us and finding peace in the vastness of the unknown. We will simply wonder together at the stories the cosmos has to tell and the silent lessons they hold for our human hearts. The human heart, a quiet, intricate mechanism, beats not only with the rhythm of life, but with an ancient, unspoken yearning. It is a yearning to transcend the fleeting dance of days and nights, to etch a whisper of our existence onto the grand, indifferent canvas of eternity. This desire, so subtle, yet so profound, is not a recent invention, nor is it a learned trait. It is something deeply woven into the very fabric of who we are, a thread of longing that runs through the tapestry of human history. For thousands upon thousands of years, since the first flicker of self-awareness in our distant ancestors, this quiet ambition has guided our hands and stirred our spirits. Imagine, if you will, the earliest humans gazing up at the same star-dusted velvet sky that cradles us now. Perhaps even then, a silent question formed in their nascent minds. How can I, a single breath in the vastness, ensure that my echo lingers? And so they began to build, not just shelters for survival, but monuments grand and enduring, crafted from the very bones of the earth. Think of the mighty stones of Stonehenge standing silent and stoic against the winds of millennia, a testament not only to ancient engineering, but to an ancient collective desire to be remembered. Or the colossal pyramids rising like mountains carved by giants, each block a silent prayer against oblivion, designed to hold the memory of kings and their reign long after their dust had scattered to the winds. These were not merely tombs of power, but enduring sculptures of memory anchors in the tumultuous sea of time. And this yearning wasn't confined to stone and mortar. It spilled into the very essence of human action. People performed great deeds, not always for immediate glory or tangible reward, but often with a silent, profound hope that their actions would ripple through generations, transforming their lives into stories that would be retold around countless fires. A warrior's courage, a leader's wisdom, an artist's vision. These were the living monuments, the echoes of a life lived with, intent designed to endure long after the physical form had dissolved. It is this innate human need for permanence, for a gentle whisper of our passage to remain, that has driven so much of our collective journey. So it is hardly a wonder, is it, that this deep-seated desire finds a particularly potent expression in the realm of scientific discovery. Consider the quiet ambition of those who dedicate their lives to unraveling the universe's deepest secrets. Their monuments are not built of stone, but of knowledge. Their legacy is etched not in grand sculptures, but in the very maps of the cosmos, in the understanding of how light travels or how stars are born. To be the one who first spots a special star, a new and previously unseen planet, or to uncover a hidden law of nature. This is a profound form of immortality. Their names become entwined with the celestial bodies they observe, or the principles they uncover whispered in classrooms and observatories for all time. Imagine the quiet satisfaction, the profound sense of having truly been here, of having added a new shining detail to humanity's shared understanding of its place in the universe. It is a silent plea against oblivion, a gentle defiance of the ephemeral nature of individual existence. This desire, though beautiful in its essence, carries with it a delicate balance, a quiet, tightrope walk between passionate pursuit and obsessive ambition. The line between wanting to contribute to the collective tapestry of knowledge and yearning, too fiercely for one's own name to be the loudest thread, can be perilously thin. What happens when the longing to be remembered, to be crowned with the laurels of discovery, overshadows the purest, most selfless pursuit of truth? This is where the gentle current of our initial yearning can sometimes transform into a powerful, almost blinding force. The very human tendency to seek confirmation, to find what we desperately hope is there, can subtly nudge our gaze. It's a quiet whisper in the mind, a silent urge to confirm a hypothesis, even when the evidence might be less than certain. And perhaps in this delicate interplay of ambition and observation lies a profound lesson, a contemplative whisper from the depths of scientific history. The universe in its boundless elegance has its own silent logic, its own intricate design. It doesn't require our fervor to prove its truths. Its facts stand on their own patient and unwavering waiting to be revealed through careful observation, through rigorous testing, and sometimes through the gentle letting go of our most cherished ideas. It is an invitation to simply wonder without the need for immediate answers or personal glory, to acknowledge that the deepest truths often unveil themselves not with a sudden flash, but with the quiet, persistent light of patient inquiry. This subtle interplay, this gentle tension between human desire and the universe's unwavering reality, will be a quiet companion on our journey tonight. We will witness how this fundamental human trait, this longing to be remembered, has shaped some of the most fascinating tales in the annals of science, tales of triumph, of perseverance, and sometimes of illusion. We will learn that the pursuit of truth, while exhilarating, demands a humility that allows us to challenge even our most deeply held beliefs. For the truth in its own gentle time will always reveal itself, proving its own undeniable existence through repetition, through consistent observation, and through the quiet, elegant simplicity of its underlying principles. And in that unfolding, there is a beauty far greater than any single name etched in history. It is the beauty of shared understanding, of collective wonder, flowing like a timeless river through the landscape of human thought. So let us gently begin our descent into the quiet whispers of the past as we look at the fascinating, yet ultimately illusory discovery of a planet that never truly existed. It is a story that begins not with a grand explosion, but with a subtle whisper of uncertainty in the cosmic dance, and a human heart eager to find an answer that would resonate through the ages. The year 1846 unfurled like a scroll of destiny, bathed in the soft, expectant glow of scientific triumph. Something astounding had just happened, a quiet revolution in the way humanity perceived its cosmic neighborhood. It was a moment of profound beauty where pure thought, like a delicate gossamer thread, seemed to pluck a hidden world from the vast, unseen depths of space. At the heart of this quiet miracle was Joseph Leverrier, a French astronomer and mathematician, a man whose mind moved with the elegant precision of the celestial bodies he studied. He had been engaged in a painstaking cosmic ballet, meticulously examining the subtle rotations of the then-known 7 planets, charting their paths with an almost devotional exactitude. But as he traced the familiar arc of Uranus, a gentle discord began to hum in his calculations. Something was off. It was like a single note in a grand symphony, subtly, persistently out of tune. Uranus wasn't quite dancing in line with the majestic gravitational theories proposed by Newtonian physics, the very bedrock of understanding the universe's clockwork. The deviations were minute, mere whispers in the vastness, but to Leverrier's discerning mind, they spoke volumes. His intellect, keen and unyielding, reasoned that there could be only one elegant explanation for this cosmic anomaly, this slight perturbation in Uranus's otherwise predictable journey. There must be an unseen hand, a celestial sibling, a planet out beyond the established orbit of Uranus, whose gentle gravitational tug was subtly altering its course. It was an act of profound intellectual courage, a leap of faith, grounded in the unshakable certainty of mathematical law. To account for this discrepancy, this tiny wrinkle in the fabric of the known universe, he did the maths. He performed calculations so intricate, so vast, that they seemed to spin a new world into existence from the sheer power of numbers alone. And then, with the quiet confidence of a prophet unveiling a truth, he declared that this eighth planet, this unseen gravitational anchor, must exist at an exact point in the night sky. He didn't just suggest. He pinpointed, with an almost impossible precision, the location of a world no human eye had ever seen. The truly incredible thing, the part of the story that still sends a gentle shiver of awe down the spine, is what happened next. News of his prediction, a beacon of pure deduction, reached the ears of Johann Gottfried Galle, a friend and fellow astronomer in Berlin. Galle, upon hearing Leverrier's almost audacious claim, didn't hesitate. He simply went to his observatory, aimed his telescope towards the precise coordinates Leverrier had provided, and began to search. And sure enough, in a single hour, as if plucked from the cosmic ether by the power of human intellect, he discovered the planet Neptune. It was almost exactly where Leverrier had predicted it would be, a testament to the profound beauty and predictive power of mathematics, a silent symphony played out across millions of miles. The scientific community, a vibrant tapestry of curious minds, went wild with this discovery. It was an event that rippled through the quiet halls of academia and echoed even in the broader public imagination. Leverrier, whose quiet deductions had given humanity a new world, was rightly celebrated for his incredible foresight. His name became synonymous with the triumph of pure reason, a symbol of humanity's growing mastery over the universe's hidden secrets. He had pulled back a curtain on the unseen, and in doing so had deepened our understanding of the cosmic order. So it is hardly surprising, is it, that just a decade later, when the same brilliant mind, Leverrier, predicted the location of a ninth planet using the very same methodology, the scientific community listened with eager ears. His past success with Neptune cast a long shimmering shadow of expectation, a silent promise that he might once again unveil a hidden world. The methodology was sound-proven. The triumph of Neptune had etched its wisdom onto the collective consciousness. If the numbers speak, a new world might be waiting. In fairness to the quiet whispers of history, he had not been the very first to suggest that such a planet nestled even closer to the Sun than Mercury might exist. The idea, like a faint echo, had been circulating for centuries, a subtle intuition born from fleeting glimpses and unresolved puzzles. As far back as 1601, the German astronomer Christoph Scheiner had claimed to have noticed a strange black spot, a tiny cosmic shadow, moving in front of the blinding face of the Sun. He, with the limited tools of his era, had claimed this ephemeral smudge was indeed a planet. In reality, it was most probably nothing more than a sunspot, a temporary blemish on the Sun's fiery skin, but the seed of an idea had been planted. Other alleged sightings had been made throughout the years, like distant unconfirmed whispers from the cosmic void. Kapell Loft in 1818, Franz von Graun in 1819, and J.W. Pastorff between 1822 and 1837 all claimed to have seen an object or objects, tiny specters orbiting the Sun. Pastorff, with a curious persistence, even claimed to have seen it at least 12 different times each instance, a new flicker of hope in the darkness. These were not rigorous, repeatable observations, but rather isolated, fleeting moments easily mistaken for other phenomena. Yet each whisper added to the collective quiet expectation that perhaps, just perhaps, a world lay hidden in the Sun's blinding embrace. The very idea of such a hypothetical planet, one so close to the Sun's inferno, began to capture the collective imagination, even sparking informal conversations about its name. In 1846, the same year Leverrier found Neptune, French astronomer Jacques Babinet suggested a name that resonated with its imagined nature, Vulcan. He drew inspiration from the Roman god of volcanoes, fire, and metalwork, a deity synonymous with intense heat and transformative power. This would have been an incredibly appropriate name, a gentle echo of its likely environment. Imagine for a moment any planet orbiting closer to the Sun than Mercury. It would have been a world of unimaginable temperatures. Mercury itself, our closest planetary neighbor, already endures blistering temperatures reaching 427 degrees Celsius. Vulcan, if it truly existed, would have been an even hotter crucible, a silent furnace spinning in the sun's fiery breath. And yet for all these tantalizing glimpses, these whispered claims and the compelling logic of Leverrier's subsequent calculations, confirmation of the planet remained stubbornly elusive. It was like trying to grasp smoke, a phantom limb of the solar system. The observations were isolated, fragmented like scattered pieces of a puzzle that never quite fit together. The quiet, persistent absence of a consistent, repeatable sighting kept Vulcan in the realm of hypothesis, a beautiful dream lingering at the edge of scientific certainty. It hung there, a question mark suspended in the brilliant glare of our star, waiting for a definitive answer that remained stubbornly out of reach. But what truly made Leverrier's claims stand out, what gave them a weight and gravitas that earlier fleeting observations lacked, was the profound and elegant methodology he had employed. It wasn't based on a fleeting glimpse through a telescope, but on the precise, unwavering logic of mathematics, the very tool that had unveiled Neptune. The story of Vulcan, therefore, is not merely a tale of a phantom planet, but a deeper narrative about the power and sometimes the pitfalls of scientific prediction, especially when the desire for discovery burns brightest. It is a quiet study in how human hope and intellectual certainty can sometimes intertwine, leading even the sharpest minds down paths of persistent, beautiful illusion. The stage was set for a quiet drama where the allure of a hidden world and the ambition of its pursuers would dance on the edge of the known universe. Let us now gently turn our gaze to the subtle dance of Mercury, the swift, elusive planet closest confidant to the Sun. It was its orbit, its tiny, persistent deviation that ultimately breathed new life into the idea of Vulcan, transforming it from a mere whisper of possibility into a compelling mathematical certainty for minds like Leverrier. The story begins not with an outright crisis, but with a quiet, almost imperceptible discord in the grand cosmic symphony. In 1845, even before his breathtaking discovery of Neptune, Leverrier had been quietly tasked by the director of the Paris Observatory with a profound challenge. It was a subtle, meticulous detective job to apply Newton's laws of physics to the precise orbit of Mercury, to see if the two, the theoretical and the observed, aligned in perfect harmony. Leverrier, with his characteristic rigor, set about this task, laying out a theoretical orbit that Mercury should take around the Sun, a graceful path prescribed by the universal laws of gravity. Once his meticulous prediction was made, astronomers with their patient eyes and finely tuned instruments observed Mercury, eager to see how well the real celestial dance matched the mathematical ideal. Only it did not. The deviation was minute, almost a negligible whisper in the vastness of space, yet it was undeniably there, a tiny, nagging inconsistency. Leverrier, ever the meticulous scholar, didn't immediately jump to grand conclusions. He tried again, reasoning with a gentle humility that perhaps his own intricate calculations, vast as they were, might have contained some minuscule error. And so in 1859, he embarked on a much more thorough study, delving deeper using multiple observed sightings of Mercury as his baseline, weaving them into his complex mathematical tapestry. Once again, he mapped out Mercury's theoretical orbit with exquisite precision. But once again, his predictions were out. Not by much, mind you, only a tiny 45 arc-seconds per century. Imagine that, a shift so minuscule, like the merest twitch of a clock hand over 100 years. Yet, it was enough. Enough to confirm conclusively that there was something subtly, undeniably weird going on. Something was gently nudging Mercury from its idealized Newtonian path. Leverrier, now utterly confident in his mathematical fortress, reached the only logical conclusion he believed possible within the framework of Newtonian physics. There must be some unseen mass, a hidden gravitational anchor, gently pulling Mercury outwards from its predicted idealized orbit. This unseen presence, he reasoned, could either be another planet, a cosmic sibling yet to be discovered, or perhaps a series of asteroids, a scattered family of smaller bodies whose combined pull was just enough to create the observed discrepancy. Given his recent stunning success at locating Neptune through pure deduction, many astronomers steeped in the elegance of Newtonian mechanics believed him implicitly. Their minds, having witnessed one miracle, were open to another. The stage was set not for a quiet contemplation, but for a fervent quest. Scientists, fueled by this renewed hope and the towering authority of Leverrier's intellect, rushed to their telescopes. They turned their patient, expectant gazes towards the blinding brilliance of the sun, seeking that elusive, unseen presence. And it wasn't long before results whispered like secrets from the cosmic depths began to come in. Spotting a planet so close to the sun was by its very nature an inherently difficult task. The sun's overwhelming glare, a fiery ocean of light, would completely obliterate the reflected shine of a tiny planet, making it all but invisible. As such, the most effective method, the most hopeful way of discerning such an object, was to patiently wait and observe the subtle darkening it caused as it traveled across the sun's face like a tiny fleeting shadow. And then, in 1859, a hopeful whisper became a triumphant shout. Edmond Modeste Lescarbot, a French amateur astronomer and physician, claimed to have seen just that. With his modest tools and a homemade observatory, a quiet testament to his personal dedication, he claimed to have spotted a small black object, a tiny cosmic silhouette, passing by the sun on the 22nd of December. It was a fleeting moment, a unique observation, but one that resonated deeply with the scientific community's expectations. Lescarbot, his heart perhaps thrumming with the excitement of discovery, immediately wrote to Leverrier. Leverrier, whose life was by now inextricably linked with the search for this elusive planet, was so taken by Lescarbot's claim that he journeyed by train to the man's home unannounced, a testament to his fervent desire for confirmation. He questioned Lescarbot meticulously, listening with an almost reverent attention to his observations. And after this quiet interrogation, Leverrier, with his unparalleled authority and a mind that had already plucked a world from the void, came to the profound conclusion that the man was telling the truth. And so, with the weight of Leverrier's endorsement, the two of them announced Lescarbot's discovery to the eager scientific community. They formally named the planet Vulcan, a name already whispered in anticipation, a name embodying the fiery crucible from which it emerged. The scientific community once again was deeply impressed, swept up in the tide of another predicted and found world. Lescarbot was bestowed with the Légion d'honneur, the highest order of merit in France, a shining symbol of his perceived achievement. He gained the privilege of speaking at meetings of learned scholars, his quiet life as a physician now illuminated by the dazzling light of cosmic discovery. There was, however, one quiet, persistent problem. The planet he had discovered, the world they had named Vulcan, didn't actually exist. It was a ghost, a beautiful illusion woven from earnest observation, mathematical certainty, and the deep human longing to fill a perceived void. The proofs of this non-existence would in time gently accumulate like soft falling snow, bearing the dream of Vulcan beneath the undeniable weight of reality. The initial triumph would slowly, subtly begin to unravel, revealing a deeper truth about the universe and about ourselves. For one, naturally, other scientists, filled with a healthy dose of skepticism and a burning desire for independent verification, wanted to take a look at this new planet Vulcan. Leverrier, ever the meticulous calculator, had used Lescarbot's observations to determine Vulcan's supposed orbit. He calculated that Vulcan must orbit approximately 21 million kilometers out from the Sun, a remarkably close embrace with our star, and that it completed its scorching journey every 19 days and 17 hours. This, he reasoned, should make it relatively easy to spot, as its transits across the Sun's face would be calculable, predictable, and thus eagerly awaited. So astronomers around the world, armed with their telescopes, pointed their patient lenses towards the Sun at the appointed times, their hearts perhaps thrumming with anticipation. But time and again Vulcan was a no-show. The predicted shadow never appeared. The sky remained stubbornly empty where a planet should be. This absence, this quiet, persistent void, troubled Leverrier deeply. It was a dissonant note in the symphony of his success, a nagging doubt that began to chip away at the edges of his certainty. And yet, despite the glaring absence, more reports of planet sightings began to trickle in. Other astronomers, perhaps influenced by the initial excitement, and Leverrier's authority, began to pour back through their historical records, gently re-examining past observations. They claimed to be matching up phenomena they had seen years, even decades ago, with the newly christened planet Vulcan. Some of these historical sightings were years out of date, mere fleeting notes in a dusty journal, not even listed as to when precisely in the year they had happened. Yet Leverrier, clinging to the hope of his mathematical certainty, still used these fragmented, imprecise records to tinker with his model. He reasoned, perhaps with a gentle self-deception, that his original calculations were just slightly off, that the maths needed a little more coaxing, a few more adjustments, and so he would predict and would not see Vulcan, and would rework his theory, and would not see it again. It was a quiet, persistent loop of hope and disappointment, a testament to the powerful influence of confirmation bias. Another piece of damning proof, a quiet, almost imperceptible whisper that grew into a resonant truth, came from Emmanuel Liais, another French astronomer. Liais claimed that by a remarkable coincidence, he had been looking at the Sun at the exact same moment Lescarbault had, but with a telescope twice as powerful. And with his superior instrument, he had seen no planet. His sky had been empty. This quiet contradiction, this direct challenge from a fellow professional, added another layer of doubt to Vulcan's already murky existence. It suggested that perhaps Lescarbault, with all his earnestness, had seen nothing more than a sunspot or a tiny dust mote on his lens or a fleeting moment of visual illusion, rather than a hidden world. Vulcan's existence continued to float through murky waters, a persistent myth, rather than a confirmed fact. Despite the mounting evidence against it, there were still renowned scientists who from time to time claimed to see it. The human mind, once convinced, can be remarkably resistant to relinquishing a cherished idea, especially one that fits so neatly into a pre-existing framework of understanding. Leverrier himself died in 1877. His brilliant mind, having bequeathed to humanity a new world in Neptune, but leaving the phantom of Vulcan unresolved. Yet just a year later, in 1878, a new flicker of hope ignited. Two well-renowned astronomers, each with a reputation for meticulous observation, both claimed to have seen Vulcan at the very same point in the sky at the very same time during a solar eclipse. Imagine the profound impact of such a seemingly compelling cooperation of sightings. During an eclipse, the sun's overwhelming glare is momentarily dimmed, offering a precious fleeting window into the region. Close to its fiery disk, a rare opportunity to spot any hidden objects. They even both claimed that the planet was reddish in color, a detail that added to the compelling nature of their reports. For a moment, the dream of Vulcan seemed to rise again, affirmed by independent, credible witnesses during the optimal viewing conditions. And yet, despite all this, despite the initial mathematical elegance, despite Lescarbault's earnest claims, despite the later seemingly corroborating eclipse sightings, Vulcan still did not exist. In science, a fundamental truth, a quiet, unwavering principle dictates that if a fact is truly true, then it is repeatable. It must be observed consistently, independently, and under various conditions, time and time again. And in spite of all these isolated observations throughout the years, Vulcan was never repeatedly observed. It was never seen during another solar eclipse, never consistently tracked across the sun's face. In time, those seemingly corroborating eclipse sightings were gently put down to calculation errors, to the misidentification of a known star, or perhaps to the powerful psychological pull of wanting to see what was expected. The phantom of Vulcan, once a vibrant promise, was slowly, quietly dissipating into the mists of scientific history. But ultimately, the one who finally gently, yet conclusively, put the idea of Vulcan to rest was a mind that dared to think differently, to imagine a universe woven from an entirely new fabric. It was Albert Einstein. He did so not by searching for Vulcan, not by poring over old observations, but by thinking of something completely gloriously revolutionary. Numerous scientists over the years had diligently, patiently attempted to see Leverrier's elusive planet Vulcan, because mathematically, they were certain it had to exist. Newtonian physics demanded that it did. Their minds, steeped in the brilliance of Newton's laws, strained to see it. And in that powerful confirmation bias, they did see it again and again in fleeting moments, in isolated observations. Just never consistently, never in the same place, and never truly in reality. They were like musicians trying to find a missing note in a symphony that simply wasn't there because they believed the score demanded it. But Einstein, with a quiet revolutionary genius, realized that it was not the cosmos that was at fault. It was rather Newtonian physics that was, in this specific instance, gently flawed. In 1915, he proposed a breathtaking new model of physics, a tapestry woven from the very fabric of space-time itself. His theory of general relativity accurately described the motion of the universe, but it relied on concepts far beyond simple gravitational pull. It spoke of the curvature of space-time of massive objects, like the sun creating dips and valleys in the cosmic fabric, and of planets simply following the gentle curves of this warped landscape. At slow speeds in the everyday world, Einstein's model looked a lot like Newtonian physics, gracefully overlapping with its well-established truths. But when you placed objects like Mercury so close to the incredibly massive sun, a different, more nuanced picture emerged. Special relativity predicted a slightly different, more precise path for their orbits. And sure enough, with a quiet elegance that was almost poetic, Einstein's model predicted the exact orbit that Mercury made around the sun, deviations and all. The 45 arc-seconds per century, that stubborn, nagging anomaly, was perfectly beautifully explained, not by a hidden planet, but by the very geometry of the cosmos itself. And with that, the case for Vulcan's existence evaporated. Under the graceful lens of special relativity, it simply couldn't exist. There could be no object next to the sun of a planetary size, for, if there were, its presence would disrupt Mercury's orbit in a way that would no longer line up with Einstein's elegant mathematics. The need for Vulcan vanished, not with a bang, but with the quiet, undeniable logic of a deeper truth. And this time, Einstein was able to prove his maths correct through rigorous tests like the famous Eddington experiment, which observed the bending of starlight around the sun during an eclipse, a direct confirmation of space-time's gentle curve. There is a profound lesson in this story, a quiet whisper from the heart of scientific endeavor. Sometimes when we want something too much, when a theoretical framework demands a particular answer, we find it. We see what we expect to see, even if it is not truly there. It is the power of human expectation, a subtle confirmation bias that can blind us to alternative truths. And sometimes, it takes a mind daring to think outside the box, to challenge our previously held beliefs, to question the very foundations of our understanding, before the truth can finally be found out. It is a testament to the courage required to dismantle a beautiful, cherished idea when faced with a more accurate, more elegant reality. As scientists, and equally as laypeople navigating the complexities of our world, it's profoundly important that we do not hold too tightly to our ideas, no matter how appealing, how logical, or how well supported they seem at first glance. The truth does not need our fervor, our passionate defense, or our desperate attempts to make it fit. It will prove itself given time and opportunities for repetition, for independent verification, for the quiet, persistent accumulation of evidence. So there you have it. The planet Vulcan, a planet of fire that was nothing but smoke and mirrors, a yearning for something that was never a reality. Newtonian physics, though, a magnificent edifice, was gently replaced by Einstein's theories of relativity, and now special relativity is here to stay, at least until it is supplanted by something even more comprehensive, a new, even more elegant tapestry of understanding. The universe, in its boundless wisdom, often reveals its secrets in its own quiet, unexpected ways, teaching us humility and endless wonder. Let us now gently shift our focus from the grand fiery embrace of our sun and the elusive phantom of Vulcan to a different kind of celestial dance, one born from human ingenuity and national ambition, a story that whispers of fleeting triumphs and quiet resignations. Far above us, circling the Earth once every 90 minutes, the Prospero satellite floats through space, a silent sentinel. The 28th of October marks a significant anniversary of its launch, a half-century since this special satellite began its solitary vigil. And though it no longer functions, a silent relic of a bygone era, it will likely remain in orbit for another 50 years, yet a testament to its enduring, if forgotten, presence. There is something strangely melancholic, yet profoundly inspiring about this unique satellite that only ever ran a couple of scientific experiments. Its story, though often overlooked, holds lessons of ambition, challenge, and the quiet beauty of legacy. But why is Prospero so unique? Why does its quiet presence in Earth's orbital attic resonate with such a particular charm? Prospero is the result of the only time a nation developed its own rocket capacity to put a satellite into space, and then later discarded that capability. It's a poignant tale of a national dream, briefly realized, then gently set aside, a unique chapter in the sprawling history of space exploration. I'm Alex Mullen, and you're watching Astrum, and today let's join together as we gently uncover the early days of space exploration history of my home nation, the United Kingdom, and the first and only time they put a satellite into space using a rocket of their own making. Today, we will quietly explore Prospero and the Black Arrow program of the United Kingdom. The UK officially joined the bustling space race in 1962, not with a triumphant roar, but with a quiet, significant step. They became the third country to operate a satellite in space after the mighty pioneers, Russia and the United States. However, that first satellite, Ariel 1, a beacon of British scientific ambition, was not launched using a UK rocket. Instead, it was carried into orbit, a guest on another's strength, by NASA, the burgeoning American Space Agency. At a time when America and the USSR were beginning to gear up for their monumental journey to the moon, their eyes fixed on a distant silvery orb, the United Kingdom, with a quiet sense of urgency, was eager not to be left behind to forge its own path among the stars. The Royal Aircraft Establishment, RAE, which was perhaps the closest equivalent the UK had to their own nascent space agency at the time, first quietly proposed the idea of developing their own rockets in 1963. Up until then, UK rocket science had been mostly military in nature, a legacy of wartime innovation and Cold War anxieties. Rockets like Blue Streak and Black Knight were developed drawing on the profound scientific knowledge of German scientists who had been brought to Britain after World War II, much like what happened in America around the same time. These powerful instruments of engineering were primarily intended to carry nuclear payloads, their purpose etched in the grim realities of geopolitical tension. However, the RAE harbored a different, more peaceful ambition. They wanted to make rockets that could gently carry satellites into space, not for destruction, but for the noble purposes of scientific discovery and communication. Their initial request was modest yet profoundly ambitious for a low Earth orbit rocket that could carry a 144-key satellite into orbit. The request, A Quiet Spark of Hope, was approved in 1964, but was quickly put on hold, a victim of earthly politics, due to an upcoming general election. A new government came in with its own set of priorities and its own gentle touch and restarted the process. But in a quiet premonition of the challenges to come, they decided to reduce the number of test flights from 5 to 3. This subtle reduction was, in hindsight, the beginning of the slow, quiet withering of the UK's rocket abilities, a delicate dream being pruned before it had even truly begun to blossom. Using the foundational technology of the Black Knight rockets, the dedicated scientists at RAE began to develop the Black Arrow. It was a 3-stage rocket, an elegant structure designed to climb into the heavens. And though it utilized much of the same core technology as its predecessor, the Black Knight, the Black Arrow, was considerably more powerful, a testament to subtle refinements and quiet innovations. It produced an initial 256 kilonewtons of thrust, a mighty push compared to the Black Knight's 96 kilonewtons. The journey of the Black Arrow was a carefully choreographed ballet of power and separation. The first stage, a colossal engine of propulsion, would carry the precious payload for the initial 2 minutes or so of the launch, providing the overwhelming force needed to escape the Earth's tenacious embrace before gracefully falling away, a discarded shell. The second stage would then ignite burning for 2 more minutes, pushing the craft higher and faster, before it too would split in half, a delicate mechanical dance, releasing the slender third stage and its precious payload into the silent void. After this separation, the third stage would burn for a final minute, a quiet, precise burst of energy propelling the satellite to its desired orbital velocity. And a minute later again, the payload and the final stage would separate, leaving the satellite alone to begin its lonely vigil around the Earth. The construction of the Black Arrow, like a sprawling, intricate puzzle, involved various parts being crafted around the United Kingdom, a testament to national collaboration. Much of the final assembly, the meticulous piecing together of this giant arrow for the heavens, took place in the Isle of Wight, a quiet island off the southern coast of England. The launch site itself, however, was located far from home, nestled in the vast open expanses of Australia, a Commonwealth country. Other test sites closer to home had been considered, whispered about in hushed tones. But in the end, it was gently decided that the risk of spent rocket parts falling upon populated locations in the UK was simply too great a practical concession to safety, and a quiet acknowledgement of the power being unleashed. However, the Wilson government of the day was navigating turbulent waters, experiencing difficult financial times. Like many nations, they were looking for ways to reduce their outgoing costs to trim the edges of ambitious projects. They had another grand project underway, one that was demanding colossal investment, the sleek supersonic airliner Concorde. And the UK government, facing the twin demands of innovation and fiscal prudence, simply didn't want to invest heavily in both programs. Ideally, they whispered, they didn't want to spend money on either. Ironically, in a decision that now carries a quiet, poignant weight, they decided that Concorde had the better long-term prospects for the UK economy than satellite technology. A tragic miscalculation, perhaps, considering that Concorde, for all its graceful speed and technological marvel, ended up grounded altogether in 2003, a beautiful bird whose wings were clipped. It wasn't that they didn't believe satellites would benefit the economy, not at all. It was a more subtle administrative challenge. No one could quite agree on who should cover the substantial development costs, a quiet, bureaucratic deadlock. On top of this financial and political uncertainty, the Black Arrow program, already navigating treacherous currents, began to run into technical problems too, like unexpected headwinds. Although its maiden flight, a crucial test of its first 2 stages, was planned for 1968, it wasn't until 1969 that the first Black Arrow finally launched. And that launch, after years of painstaking effort, was unfortunately a failure. An electrical fault, a tiny unseen flaw, caused some of its combustion chambers to pivot unexpectedly, causing the rocket to roll erratically like a ship lost at sea. It ended up disintegrating, a heartbreaking spectacle, and was ultimately completely destroyed, a quiet end to a soaring ambition. The second launch, a test of the first two stages, again went off successfully, a momentary sigh of relief. But the Black Arrow's third and final test launch, where it first attempted to reach a full orbit, was also a failure. Its second stage, a crucial heart of the rocket, had an oxidizer that failed to pressurize correctly. This vital malfunction meant that the second stage cut out early, prematurely silencing its powerful roar. And so, the whole rocket with its mock payload, a symbol of unfulfilled promise, failed to reach orbit. In this time, while Britain struggled, other nations quietly, steadily forged ahead. France, Japan, and China all successfully launched satellites using their own rockets, painting their own lines across the cosmic canvas, leaving Britain for a moment in their silent wake. On the 29th of July, 1971, the UK government, facing mounting costs and persistent challenges, made the difficult decision to cut its losses and cancel the Black Arrow project. It was a profound blow to the dedicated men and women of the RAE, a quiet shattering of a long-cherished dream. However, by this time, the fourth Black Arrow, a completed marvel of engineering, had already been constructed and shipped all the way to Australia, patiently awaiting its turn. And accompanying it was its precious cargo, the satellite. In a final gentle concession, the government, perhaps swayed by the completion of the hardware, finally gave the go-ahead for this final bittersweet launch. This satellite, named with a quiet purpose, was designed to test the critical technologies necessary for communicating with satellites in orbit. As such, it was packed with intricate instruments, tape recorders to capture and store data, a micrometeor detector designed to measure the frequency of tiny, almost imperceptible particles in space, and multiple designs for solar cells, each a tiny experimental patch to see which would be the most effective at converting sunlight into life-giving power in the harsh environment of space. Initially, this satellite had been given a different name, a lighter, more whimsical one. The RAE had dubbed it Puck, continuing a gentle tradition at the time of naming RAE satellites after Shakespearean references. Puck, like its predecessor Ariel, were both mischievous fey characters in Shakespearean plays. They were beings of the air of pranks and of magic light and ethereal. But when the project got canceled, a profound shift occurred in the hearts of the RAE team. They quietly, poignantly changed the name of the satellite from Puck to Prospero. Prospero, a powerful sorcerer in Shakespeare's play, The Tempest, was a master of magic, commanding spirits and conjuring storms. But ultimately, in a gesture of profound resignation and acceptance, he gave it all up, renouncing his magic to become a normal human, returning to the quiet, ordinary world. It was a sharp, almost heartbreaking indicator for how the RAE team must have felt. Though they would be allowed to launch their very last rocket, they knew with a quiet certainty that they would never do so again. Britain was, in essence, giving up on its own space race, laying down its wand. It would in the future pay for other nations to carry its satellites into space, as this was considered more economical, a pragmatic, if emotionally costly decision. To the RAE scientists, it must have felt like they were giving up the magic quietly, letting go of a dream they had so passionately pursued. And this quiet relinquishment, this bittersweet acceptance, made the successful launch of Black Arrow and Prospero on October 28, 1971, all the more poignant. Before this point, a Black Arrow had not carried a payload all the way to low Earth orbit successfully. And now, just when it had finally proven its viability, its capability to reach the stars with its own strength, it was ended. It was a quiet triumph overshadowed by the knowledge that it was also a final farewell. Admittedly, Prospero's launch didn't go completely smoothly. There was a small, unsettling hiccup. When the third stage of the Black Arrow rocket gently came away, one of its thrusters, by some unforeseen quirk, kept firing and clipped Prospero on the way past a tiny, almost imperceptible kiss of misfortune. Fortunately, while this knocked off one of Prospero's 4 antennas, a minor disfigurement, the satellite maintained a stable orbit, and was able to go on to have a successful mission, transmitting its data faithfully. It taught British scientists much about designing satellites for space, a knowledge that would come in useful as Britain quietly, steadily went on to specialize in the field of satellite technology, becoming a leader in a different aspect of the cosmic endeavor. Unlike in other nations like the United States, the successful launch of their first satellite, a profound moment of national achievement, did not even make the UK front-page news. The public, largely unaware of the subtle drama unfolding in orbit, didn't really notice it. It happened a quiet event in the grand scheme of things. It was a full 2 days later before any newspapers even mentioned it, a fleeting note in the back pages. The UK government, in its official capacity, acknowledged that the successful launch was excellent news, a job well done, but crucially, it did not restart the program. And so Britain became the 6th nation to launch a satellite into space, using its own rocket, a quiet milestone, but one that seemed destined to be just that, a single isolated achievement. In 1973, Prospero's tape recorders, their magnetic reels spinning tirelessly, finally stopped working. It could still be contacted, its faint signal a testament to its enduring power. But government scientists eventually stopped doing so when they quietly closed their satellite monitoring station in 1996. Prospero was officially deactivated, its formal mission complete. However, it didn't immediately go silent. Amateur satellite enthusiasts, listening with their patient, dedicated ears, continued to contact Prospero until about 2004, where its faint signal, powered by its enduring solar panels, could still be heard, a final whispered message from a forgotten pioneer. As we near the end of October 2021, we approach the 50-year anniversary of Prospero's launch, a quiet moment of remembrance for a forgotten trailblazer. Although Prospero has now gone silent, its faint echo swallowed by the cosmic noise that might have been the quiet end for Prospero and the Black Arrow project, a tale neatly filed away as a historical footnote. But then there came an unexpected twist in the tale, a gentle turn of fate that brought a forgotten dream back into the light. The universe, in its boundless wisdom, often weaves stories with threads of time that stretch far beyond our immediate sight, binding past and future in unexpected ways. For almost 50 years, Prospero and the Black Arrow program seemed destined to be a mere footnote, a failed experiment, a poignant symbol of an effort that was perhaps doomed before it even began. Their legacy for decades seemed confined to the dusty annals of history, a quiet echo of a dream gently given up. But then, as if stirred from a long slumber by a cosmic whisper, the tide began to turn, and their story proved much more influential than any of the RAE scientists could have ever predicted at the time. Thanks to the massive growth of the space industry in the 2010s, a new wave of enthusiasm and innovation sweeping across the globe, the UK government, after decades of quiet absence, decided to gently re-enter the cosmic arena. It created the UK Space Agency, a new beacon for national ambition, and is now building several spaceports, silent launch pads, for future dreams to begin developing once again, its capability for rocketry. It is a quiet return to a path once abandoned, a rekindling of a long-dormant flame. And thanks to the incredible advances made in satellite technology in the intervening years, satellites are now much smaller, far more nimble than they used to be a few decades ago. As such, only a smaller rocket is needed to carry such payloads into low Earth orbit. A rocket, surprisingly, just like Black Arrow. In fact, the Black Arrow's design, once deemed obsolete, now stands as a quiet marvel of foresight. It is so ideal for this new niche, this precise requirement, that the Edinburgh-based space technologies company Skyrora has based their rockets heavily on its design. Their Skyrora XL rocket, a testament to enduring British ingenuity, has remarkably similar dimensions to the Black Arrow and even uses the same type of fuel, a robust mix of kerosene and hydrogen peroxide. It's as if the spirit of Black Arrow, after half a century, has quietly found its perfect echo in a new generation. In 2018, In a beautiful act of homage and respect, Skyrora acquired the remains of Black Arrow R3 to display in their offices. It stands as a silent monument, a tangible link to the legacy of this great rocket inspiring new minds. And crazily enough, as part of a grander effort to gently remove space debris from orbit, they even have plans to find Prospero, that silent, lonely sentinel, and bring it back down to Earth intact. Imagine that, a homecoming for a satellite that seemed destined to drift forgotten through the cosmic currents forever. So perhaps Prospero will not end up lonely and forgotten after all. Its silent vigil might one day end with a gentle return to its home planet, a tangible symbol of a dream reclaimed. Although it seemed for almost 50 years that Prospero and Black Arrow were a mere footnote, a failed experiment as part of an effort that was doomed before it even began. Their legacy is proving much more influential than any of the RAE scientists could have predicted at the time. And perhaps the magic, that spark of innovation and daring, does not need to be given up after all. The story of Black Arrow and Prospero is a quiet testament to a profound truth. If I have seen further, it is by standing on the shoulders of giants, just like Isaac Newton, whose towering intellect built on the work of countless others. The grand Apollo program, with all its iconic achievements, did not stand alone in the cosmic void. Its triumphs, its breathtaking milestones, would not have been possible if it had not been for the important missions that ran before it and alongside it. It built on the understanding learned from those quieter earlier missions, expanded on their technology, and drew on the expertise of the people who worked on them, a gentle continuity of human effort. I'm Alex Molin, and you're watching Astrum. Join with me today as we quietly examine two of those vital early programs, the foundational steps that allowed humanity to dream bigger: Project Mercury and Project Gemini. We will gently investigate how these pioneering endeavors helped a fledgling NASA to gain a greater understanding of how to put a man on the moon. Slowly, carefully, one step at a time, I hope by the end of this journey, I will have earned your quiet appreciation, your like, and your subscription as we delve into the tender beginnings of human spaceflight. NASA as an institution, a towering symbol of human ambition in space, has not, in the grand scheme of things, been around forever. Its very existence is a relatively recent chapter in humanity's long history. It was only created in 1958, a direct and focused response to the Soviet Union's quiet yet startling triumph of launching the Sputnik satellite about a year earlier. Sputnik's insistent beeps echoing across the globe served as a profound wake-up call, a gentle yet firm nudge that a new frontier had been opened and the United States needed to lead the way. However, it's not entirely accurate to say that NASA was born completely new, springing forth from nothingness in 1958. When U.S. President Eisenhower signed off on the formation of NASA, he did so by quietly yet strategically combining several already existing programs and institutions. It was a gentle amalgamation, bringing together disparate threads into a coherent, powerful tapestry. There was the NACA, the National Advisory Committee for Aeronautics, a long-standing body dedicated to flight research. There was the U.S. Army's Ballistic Missile Agency, with its formidable expertise in rocketry. And crucially, there were the brilliant German scientists who had worked on ballistic missiles for Germany during World War II, many of whom had been brought to America after the conflict, their knowledge a quiet, invaluable asset. Beyond that, the U.S. Air Force had been working on a Man in Space Soonest program, a nascent, ambitious effort to put a human into orbit. This program, along with some of their facilities, was also quietly transferred to the newly formed NASA. These, alongside other various government projects, provided the solid, if somewhat fragmented, foundation for NASA, allowing it to build quickly and purposefully. However, amongst all these disparate threads, there remained a crucial quiet gap. There wasn't within this newly assembled framework a clear established way to get a human into sustained orbit around the Earth. The closest existing capability was the X-15 program of NACAR, a remarkable endeavor in its own right. The XU-15, a sleek, powerful research airplane, was designed to skim the very edges of space, pushing the boundaries of atmospheric flight. In the early 1960s, it broke records, flying to an astonishing height of around 105 kilometers and achieving speeds of over 6,000 kilometers per hour. A later X-15 even surpassed this breaking 7,200 kilometers per hour, a record that holds to this day for the fastest crude-powered aircraft. This was an incredible feat, pushing past the commonly accepted Kármán line of 100 kilometers, which is the international definition of space. But while the X-15 could briefly touch the void, it was really the limit of an airplane, a fleeting visitor rather than a resident of space. Something more profound, something entirely new, would need to be developed to get a human truly into sustained orbit and, ultimately, to the moon. And so, with a quiet determination, NASA began its very first dedicated project to get a human properly truly into space, Project Mercury. Project Mercury's mission was, in essence, a continuation of that Man in Space Soonest program, now given a focused purpose. As its very name suggests, its core objective was to get a man into orbit and back safely, ideally before the Soviet Union, whose quiet, relentless progress served as a constant spur. This, however, would be no easy task. It was a journey fraught with unknown dangers, a quiet step into a realm utterly alien to human experience. Riding a rocket into space meant an astronaut would need to deal with the crushing force of G-forces, the intense, bone-rattling vibrations of launch, and the terrifying risk of explosion from riding on what was basically a repurposed military missile. Then there was the chilling threat of catastrophic burning up on re-entry as the capsule plunged back into Earth's fiery atmosphere. Scientists also whispered quietly about other less understood dangers. The unknown effects of radiation once an astronaut left the protective embrace of the atmosphere, and even the unlikely yet terrifying possibility of a micrometeor, a tiny cosmic bullet striking the delicate ship. While some of these whispered threats proved to be negligible, the odds of being hit by a meteor, for instance, turned out to be very small. A gentle sigh of relief. The rest were very real dangers to a human life, profound challenges that needed to be met with ingenious solutions. The rockets NASA used for Project Mercury were the Redstone rocket, which was later replaced by the more powerful Atlas rocket. Both of these magnificent machines were originally designed as military missiles instruments of destruction, now quietly transformed for a purpose of profound discovery. The Redstone in particular was a direct descendant of the German V-2 rocket, a terrifying weapon developed for use in war. When the Second World War ended, America quietly strategically brought German scientists over and put them to work developing American weapons and technology. Among them was Wernher von Braun, a towering figure in rocketry who became a chief engineer at NASA. He was instrumental in helping develop the rocket technology, not only for Project Mercury, but later for the colossal Saturn V of Apollo, a quiet architect of humanity's journey to the stars. The core idea for Project Mercury was elegant in its simplicity, yet terrifying in its execution for a launch vehicle to gently carry a small pod up to a height of 161 kilometers, shedding boosters and unneeded sections along the way, like a snake shedding its skin. Once in space, the pod would orbit the Earth, getting as high as 280 kilometers at the highest point in its elliptical orbit. After completing its silent, solitary journey around the planet, it would then use its own small retro boosters to gently slow down and begin its re-entry into the Earth's atmosphere. The challenge of re-entry was immense, a fiery crucible where the capsule would need to survive frictional heat that could get as hot as 1,600 degrees Celsius, a temperature that could melt steel. After enduring this fiery trial, parachutes like delicate blossoms unfurling would open and slow the pod's descent, culminating in a gentle landing in the ocean, where it would be retrieved by waiting ships, a small island of triumph amidst the vast waters. The process demanded absolute precision, a silent choreography of events. Boosters would need to jettison at precisely the correct time to keep the weight down, a critical element in achieving orbit. This didn't always happen perfectly, a quiet reminder of the immense complexity involved. NASA was also trying out new ablative heat shields, a revolutionary concept at the time. Rather than completely preventing heat absorption, these innovative shields were designed to absorb a large amount of heat and then gently burn it off as a gas, carrying the excess heat away with it dissipating the fiery energy. Obviously, if you miscalculated how much heat shield you would need, your precious craft would simply run out, and you, the brave traveler within, would burn up in a horrifying blaze. To counter such terrifying possibilities, redundancies, silent backup systems would need to be built into the rocket in the event of any malfunction, a quiet promise of safety while a human life was on board. A rocket-powered escape vehicle, a kind of dramatic ejector seat for the entire capsule, was built into the spacecraft, a final desperate option for survival. The entire process, every step of this delicate dance, had to be thoroughly tested before they could even contemplate a crewed mission, a human life entrusted to such fragile, powerful machines. The very first effort, in August 1959, did not go well. A quiet stumble at the very beginning of the journey. Due to an incorrectly installed power plug, a tiny, seemingly insignificant flaw, the first Mercury Redstone rocket, affectionately known as Little Joe 1, only got about 4 inches off the ground before dropping back down on the landing pad, a rather ignominious start. Future launches, however, had mixed results. Some soaring, some stumbling, each one a painstaking lesson. Von Braun, with his methodical German precision, ran 20 tests in all between 1959 and 1961. Most of these tests were uncrewed silent journeys into the void. Except for a crucial few, where trained monkeys and chimpanzees occupied the pod, quiet, unwitting pioneers, their small brave lives entrusted to the unknown. Von Braun, with a deep sense of responsibility, wanted to be absolutely sure of success, to have every variable accounted for before allowing a human to go up in one of his rockets. While his caution was indeed excellent scientific practice, a profound commitment to safety, it came at a price, a quiet cost in the unfolding space race. In April 1961, Russia, with a quiet, stunning efficiency, beat America to the punch by successfully launching cosmonaut Yuri Gagarin into orbit, making him the first man in space. It was a momentous achievement, a psychological blow to American pride, and a stark reminder of their competitors' formidable capabilities. Von Braun's first human launch with brave astronaut Alan Shepard came just 1 month later. Although this was still only a suborbital flight, a brief leap into the edge of space, rather than a full orbital circumnavigation, it was a significant step for America. But the Russians had already claimed the crucial firsts. They got the first satellite into space, and now the first human into orbit. The U.S. was worried, a quiet anxiety settling over the nation, spurring them on to even greater efforts. Project Mercury ultimately ended up launching 6 human flights, 2 on Redstone rockets and 4 on Atlas rockets, all of which were remarkably successful. Each one a testament to the courage of the astronauts and the ingenuity of the engineers. And although they didn't get into space soonest, as had been their initial fervent goal, they learned incredibly important things. They learned about the delicate art of launching rockets, about enduring the strange, silent environment of space, and about surviving the fiery, terrifying process of re-entry. These were vital foundational lessons, etched not just in data, but in the experiences of brave individuals. However, when NASA announced the monumental Apollo program in 1960, with its audacious, almost unbelievable intention to reach the moon, it became clear with a quiet, undeniable clarity that far more knowledge would be needed. Mercury, for all its triumphs, had seen its final mission put an astronaut in space for a day and a half, a significant achievement in itself. But a trip to the moon and back would take a grueling 8 days, a vastly different scale of endurance and complexity. Also, NASA, with careful consideration, decided the best way to get to the moon would be to use the Lunar Orbit Rendezvous AER method. This plan, elegant in its efficiency, required them to perform perhaps the most difficult, most intricate maneuver in space travel: docking with another object in orbit. They hadn't even achieved this delicate cosmic ballet around Earth yet, let alone in the distant, unforgiving realm of the Moon. The Lunar Orbit Rendezvous method consisted of a lunar module detaching from a command and service module, a smaller craft gracefully separating from its larger parent. The lunar module would then descend a silent lander to the Moon's surface, carrying its precious cargo of astronauts. Once their quiet exploration of the lunar landscape was complete, it would then meet back up with the command and service module, which would have remained patiently orbiting the Moon. Once all the astronauts and their invaluable samples were transferred back to the command module would travel alone, a solitary vessel, back to Earth before finally splashing down gently in the ocean, a triumphant return. This intricate dance demanded not only precise maneuvering, but also a new set of skills for the astronauts. They would also need to practice doing spacewalks, extravehicular activities, or EVAs, in case work on the outside of a spacecraft became necessary during the long transit through the vacuum of space. And finally, more practice would be needed with re-entry techniques, particularly touching down at a pre-selected location on land, though in the Apollo missions, this last idea was quietly dropped in favor of ocean landings. On top of all these immense challenges, the Soviet Union, their quiet competitor, was still ahead, their footsteps echoing loudly in the cosmic race, and America, with a sense of urgency, needed to catch up. So while the Apollo team, with their ambitious visions, set to work developing its colossal rockets and intricate modules, these extra crucial challenges were handed off to a support mission to work out the intricacies. The mission was given the gentle, evocative name of Project Gemini. Project Gemini, named with a quiet elegance, took its inspiration from the constellation of the Twins, a fitting symbol for a mission that would often see two astronauts working in tandem, learning to navigate the intricate dance of space. Its primary purpose was clear yet profoundly challenging: to bridge the vast gap between the foundational lessons learned from Project Mercury and the audacious, almost unimaginable leap required for the Apollo missions to the Moon. It was a crucial stepping stone, a silent school in the heavens designed to teach NASA, and indeed humanity, the intricate ballet of orbital rendezvous and docking, the delicate art of spacewalks, and the profound endurance required for extended stays in the alien embrace of space. The challenges were immense, each one a mountain to climb before the lunar journey could even begin. First, there was the sheer duration of spaceflight. Mercury missions, while groundbreaking, had been relatively brief, mere fleeting glimpses into the void. A trip to the Moon, however, would demand days, even weeks of continuous operation in a hostile environment. Far from the comforting embrace of Earth, astronauts would need to learn to live, work, and even sleep in zero gravity, to manage their resources meticulously and to maintain their physical and mental well-being over prolonged periods of isolation and confinement. This was not just about survival. It was about thriving, about turning the capsule from a mere vehicle into a temporary home. Then came the intricate dance of rendezvous and docking. This was arguably the most critical and complex skill to master. Imagine two tiny specks hurtling through the vast, silent expanse of space at thousands of miles per hour, yet needing to gently, precisely meet and connect. It was like trying to thread a needle from miles away with both the needle and the thread, moving at incredible speeds. The Apollo mission plan, with its lunar orbit rendezvous, hinged entirely on this capability. If the lunar module couldn't detach from the command module, descend to the Moon, and then successfully redock with it in lunar orbit, the entire mission would be impossible. Gemini was tasked with perfecting this delicate cosmic ballet around Earth, a dress rehearsal for the grand performance around the Moon. And finally, there was the challenge of extravehicular activity, EV, or as it is more commonly known, the spacewalk. The very idea of stepping out of the protective shell of a spacecraft and into the utter vacuum of space was, at the time, terrifyingly unknown. What would it feel like? How would the human body react? Could an astronaut effectively work, manipulate tools, and perform tasks while floating untethered in the infinite void? The Apollo missions would require spacewalks for various tasks, from inspecting the spacecraft to retrieving samples on the lunar surface. Gemini was to be the proving ground, the first tentative steps into this new, exhilarating, and dangerous frontier. To achieve these ambitious goals, NASA needed a new spacecraft, one more robust and versatile than the Mercury capsule. The Gemini spacecraft was in essence a scaled-up version of its predecessor, a more capable vessel designed to accommodate 2 astronauts, allowing for longer missions and more complex operations. It was a marvel of engineering, a testament to the rapid advancements in aerospace technology. Its launch vehicle was the Titan II GLV Gemini launch vehicle, a powerful rocket originally developed as an intercontinental ballistic missile, ICBM, for the U.S. Air Force. Like the Redstone and Atlas rockets before it, the Titan II was repurposed for peaceful exploration, its destructive potential transformed into a vehicle for human endeavor. This continuity, the quiet evolution of military technology into tools for discovery, is a recurring theme in the early days of spaceflight. Project Gemini officially began in 1961, and its first uncrewed test flight, Gemini 1, took place on April 8, 1964. This initial flight was a quiet yet crucial step. Its primary objective was simply to test the structural integrity of the Gemini spacecraft and the Titan II rocket. The spacecraft was not designed to separate from the rocket, nor was it intended for re-entry. Instead, it remained attached to the second stage of the Titan II orbiting Earth for 3 days before burning up in the atmosphere, a silent, fiery end to its inaugural journey. It was a success, a quiet affirmation that the basic design was sound. The second uncrewed test flight, Gemini 2, launched on January 19, 1965. This mission was designed to test the spacecraft's heat shield and its ability to withstand the intense heat of re-entry. Unlike Gemini 1, this spacecraft was meant to separate from the rocket and perform a suborbital flight, splashing down in the Atlantic Ocean. The mission was a success, with the spacecraft performing as expected during re-entry and splashdown, providing crucial data for future crewed missions. These uncrewed tests, though lacking the dramatic flair of human spaceflight, were the silent, painstaking groundwork upon which all future triumphs would be built. Then came the moment of truth, the first crewed mission of Project Gemini, Gemini 3, launched on March 23, 1965. Aboard this spacecraft were 2 legendary astronauts, Gus Grissom, a veteran of Project Mercury, and John Young. Their mission was relatively short, a mere 3 orbits around Earth, lasting just under 5 hours. But within that brief window, they accomplished several critical objectives. They tested the spacecraft's maneuverability, performing the first orbital changes by a crewed spacecraft. Grissom, with a quiet sense of humor, famously named the capsule Molly Brown, a nod to the unsinkable Molly Brown, a character from the Titanic disaster, perhaps a subtle jest at his previous Mercury capsule, Liberty Bell 7, which had sunk after splashdown. The mission was a resounding success, proving the Gemini spacecraft's capabilities and paving the way for longer, more ambitious flights. The very next mission, Gemini 4, launched on June 3, 1965, just 2 months after Gemini 3, marked a truly historic moment. Aboard were astronauts James McDivitt and Ed White. While McDivitt remained inside the capsule, White embarked on a daring venture, America's first spacewalk. It was a breathtaking moment, a human stepping out into the vast, silent ocean of space, tethered only by a slender umbilical cord. The spacewalk lasted a mere 23 minutes, a fleeting moment in cosmic time, but its impact was profound. White, in his exhilaration, famously described it as the greatest experience of my life. He used a handheld maneuvering unit, a small experimental device, to propel himself gently through the vacuum, demonstrating the feasibility of working outside the spacecraft. The images of White floating against the backdrop of Earth, a tiny human against the immense canvas of the cosmos, captivated the world, inspiring awe and wonder. However, the spacewalk was not without its quiet challenges. White found it surprisingly difficult to maneuver and control his movements in the frictionless environment. He also struggled to re-enter the capsule, a subtle reminder of the unforeseen complexities of working in space. These initial difficulties, though minor in the grand scheme, provided invaluable lessons for future EVAs, highlighting the need for better training, improved maneuvering units, and more efficient procedures for ingress and egress. It was a quiet acknowledgement that while the human spirit was eager to explore the physical realities of space, demanded meticulous preparation and adaptation. Following Gemini 4, NASA embarked on a series of missions designed to master the art of orbital rendezvous and docking. This was the core objective of the program, the linchpin for the Apollo lunar missions. Gemini 5 launched on August 21, 1965, with astronauts Gordon Cooper and Pete Conrad, aimed for an ambitious 8-day endurance record, surpassing the previous record set by the Soviet Union. This mission was also intended to perform the first space rendezvous, attempting to meet with a deployed target vehicle. While they successfully broke the endurance record, proving that humans could indeed survive and operate in space for extended periods, the rendezvous attempt was hampered by a malfunction in the target vehicle. It was a quiet setback, a reminder that even in the meticulously planned world of spaceflight, unforeseen glitches could arise. The subsequent missions, Gemini 6A and Gemini 7, launched in December 1965, became a pivotal moment in the rendezvous efforts. Gemini 6A, commanded by Wally Schirra and piloted by Tom Stafford, was initially planned to dock with an Agena target vehicle. However, the Agena failed to launch, leading to a quick, ingenious decision by NASA. They decided to launch Gemini 7 with astronauts Frank Borman and Jim Lovell for a record 14-day endurance mission, and then, while Gemini 7 was still in orbit, launch Gemini 6A to rendezvous with it. This audacious plan, a testament to NASA's flexibility and determination, resulted in the first successful rendezvous of two crewed spacecraft in orbit. The two capsules flew in formation, sometimes as close as 1 foot apart, a breathtaking display of precision flying. While they did not dock, the successful rendezvous was a monumental achievement, proving the feasibility of orbital operations crucial for Apollo. The lessons learned from Gemini E, A, and 7 were profound. They demonstrated that astronauts could accurately maneuver their spacecraft in orbit, bringing two vehicles together with incredible precision. This was a critical step, a quiet affirmation that the lunar orbit rendezvous strategy was indeed viable. The 14-day mission of Gemini 7 also proved the long-duration spaceflight capabilities of humans, providing invaluable data on the physiological and psychological effects of extended periods in microgravity. Astronauts learned about resource management, waste disposal, and maintaining physical fitness in a confined environment, all vital for the much longer lunar missions. The next series of missions from Gemini 8 to Gemini the Brood focused on refining rendezvous and docking techniques and expanding the scope of spacewalks. Gemini 8 launched on March 16, 1966, with Neil Armstrong and David Scott achieved the first successful docking in space. They connected with an uncrewed Agena target vehicle, a monumental milestone. However, shortly after docking, the spacecraft began to spin uncontrollably due to a stuck thruster, putting the lives of the astronauts in grave danger. Armstrong, with his characteristic calm under pressure, managed to undock the Gemini capsule from the Agena and regain control, preventing a catastrophic outcome. This harrowing incident, a quiet reminder of the inherent risks of space exploration, provided crucial lessons on emergency procedures and spacecraft control. Subsequent Gemini missions continued to push the boundaries. Gemini Santiago AA, with Tom Stafford and Gene Cernan, attempted a rendezvous with a new target vehicle, but encountered issues. Cernan also performed a challenging spacewalk, which, while successful, highlighted the immense physical exertion required for EVAs. His visor fogged up, and he experienced extreme fatigue, a quiet testament to the unexpected difficulties of working in the vacuum. These experiences led to significant improvements in spacesuit design and EVA procedures for later missions. Gemini X, with John Young and Michael Collins, achieved a dual rendezvous docking with one Agena target vehicle, and then using its propulsion to reach a higher orbit to rendezvous with another Agena. Collins also performed 2 spacewalks, demonstrating the increasing proficiency of astronauts in extravehicular activities. Gemini Ambine, with Pete Conrad and Richard Gordon, achieved the highest Earth orbit ever reached by a crewed spacecraft at the time, utilizing the Agena's engine to propel them to an apogee of over 1,300 kilometers. Gordon performed a challenging spacewalk tethered to the spacecraft, further refining EVA techniques. Finally, Gemini Tarantula, the last mission of the program, launched on November 11, 1966, with Jim Lovell and Buzz Aldrin. This mission was specifically designed to address the challenges of spacewalks. Aldrin, with his meticulous preparation and innovative techniques, performed a highly successful series of EVAs, totaling over 5 hours. He demonstrated that astronauts could work effectively in space using tethers and foot restraints to anchor themselves, overcoming the difficulties of weightlessness. His spacewalks were a triumph, proving that humans could perform complex tasks outside the spacecraft, a vital capability for the lunar landings. By the time Project Gemini concluded in November 1966, it had achieved all its primary objectives, and then some. It had successfully demonstrated long-duration spaceflight. Astronauts proved they could endure missions lasting up to 14 days, providing crucial insights into human physiology and psychology in space, rendezvous and docking. The ability to bring 2 spacecraft together and connect them in orbit was perfected, a fundamental skill for the lunar orbit rendezvous. Extravehicular activity, EVA. Astronauts learned to perform spacewalks, demonstrating the feasibility of working outside the spacecraft and refining techniques and equipment. Precision landing. While the Apollo missions ultimately opted for ocean landings, Gemini refined the ability to land in a specific predetermined location, a valuable skill in itself. The quiet, persistent efforts of Project Gemini provided the essential knowledge and experience that would make the Apollo program possible. It was the crucial bridge, the silent school that taught NASA how to go to the moon. The astronauts, engineers, and scientists of Gemini, with their quiet dedication and unwavering courage, laid the groundwork for humanity's greatest adventure beyond Earth. Their legacy is not etched in grand monuments, but in the very fabric of space exploration, a testament to the power of incremental progress and the relentless pursuit of knowledge. Without Gemini, Apollo would have remained a distant dream, an unreachable star. It was the quiet, methodical work of the Gemini program that transformed that dream into a tangible reality, step by careful step. The Apollo program, a name that echoes through the corridors of human history with a profound resonance, stands as an iconic testament to what collective will and scientific ingenuity can achieve. To this very day, the landmarks set by the Apollo missions remain unsurpassed, like silent monumental peaks that humanity has yet to scale again. It is still the only program to get a human beyond a low Earth orbit, an achievement that lifts our gaze beyond our immediate celestial neighborhood and into the deeper cosmos. With recent efforts being made by some nations and even private entities to return people to the moon, by as soon as 2024, a date now quietly slipping a little further into the future, a gentle reminder of the immense difficulty of such endeavors. It seems like a particularly poignant idea to look back at mankind's first giant leap, to revisit that initial journey to our closest celestial neighbor. But what truly drove humanity with such immense purpose and sacrifice to visit the moon in the first place? And what profound lessons did we learn once we were there? Gazing back at our pale blue home from a silent alien world, there is so much to quietly discuss, so many threads to gently unravel. The program itself consisted of 12 crewed flights, and over a dozen unmanned ones, each a carefully orchestrated step in a grand cosmic ballet. There were immense challenges, moments of breathtaking breakthrough in technology, periods of soaring triumph, and tragically, moments of profound sorrow. I'm Alex Molin, and you're watching Astrum. Join with me as today we explore the first tender steps in getting a man on the moon with the Apollo program. The introduction to this new series, I'm planning on this incredible group of missions, a journey into the heart of human aspiration. NASA's Apollo program was and still is a colossal undertaking, a testament to what a nation can achieve when unified by a singular audacious goal. It was the single largest research and development program that has ever been conducted by a nation during peacetime. Imagine the sheer scale during its peak. NASA was quietly employing an astonishing 400,000 people, a silent army of dedicated minds and hands. It drew on the support of 20,000 different industrial companies and universities, weaving together a vast, intricate network of expertise and resources. And perhaps most strikingly, it represented a staggering 4.4% of the entire U.S. government's budgetary spending during its most intense period, given that nowadays, NASA only represents about 0.5% of the U.S. government spending. This raises an important quiet question. Why was the U.S. so singularly focused, so utterly committed to achieving this almost impossible goal? What was the silent driving force behind such an immense national effort? Firstly, we must gently understand a little of the context that led up to the creation of the Apollo program, and that begins with the chilling undercurrent of the Cold War. In the immediate aftermath of World War II, a new kind of tension began to subtly rise between the two burgeoning global superpowers, the United States and the Soviet Union. Each wanted to prove that their nation, their ideology, was inherently superior, not just on battlefields, but across every conceivable frontier, including the silent expanse of space. This was more than a mere rivalry between two nations striving to compete. It was a profound ideological struggle. Due to deeply ingrained political differences, each side saw the success of the other as an existential threat to their very way of life. America was quietly worried that if the Soviet Union did too well, it could herald the end of capitalism and democracy as they knew it. Conversely, the USSR was deeply concerned that if it didn't do better than America, it could spell the end of the communist dream, a quiet failure of their grand experiment. Each side viewed the other with deep suspicion, a veil of mistrust shrouding their interactions, and each was adamantly determined that they would not be left behind in any arena, especially one so symbolic as space. And so it was with great alarm, a quiet tremor of fear that rippled through the American people that on October 4th, 1957, the USSR, quietly yet triumphantly, successfully launched the first ever artificial satellite to orbit the Earth, Sputnik 1. Sputnik, a mere polished sphere emitting persistent haunting beeps, weighed 83 kilograms, a remarkable feat. Considering it was 8 times the size of any satellite the U.S. was even contemplating launching at the time. It circumnavigated the Earth an astonishing 440 times. During the 3 months it remained in orbit, its faint signals a constant, undeniable presence in the night sky. By sending signals to and from it, Soviet scientists were able to use Sputnik to acquire invaluable information about the density of Earth's upper atmosphere and its ionosphere, quietly gathering scientific data from the very edge of space. The rocket that launched Sputnik 1 was called the R-7, a powerful machine capable of producing an immense 4.4 million newtons of thrust. American rockets, by comparison, could only muster a paltry 670,000 newtons of thrust. This technological breakthrough, this silent demonstration of superior rocket power, profoundly unsettled the American people for 2 compelling reasons. Firstly, in an era where the chilling threat of nuclear war was never far away, knowing that an enemy nation had access to such incredibly powerful rockets made Americans feel acutely vulnerable. It seemed perfectly possible a terrifying silent whisper in the back of their minds that such rockets could easily carry devastating nuclear payloads instead of innocent scientific ones. This was a valid concern, as the R-7 was indeed designed with a nuclear payload in mind, its true purpose, rooted in military might. And up until that point, the U.S. had never truly worried about such attacks on their home soil, cushioned by their vast geographical distance from other nations. But now the oceans no longer seemed to offer protection. But more than that, more than the military threat, Americans were deeply worried that the Soviet Union was advancing further than them in terms of science and technology, that they were losing the ideological race not just on the ground, but in the very heavens. To reassure the people, the then unelected President John F. Kennedy quietly yet passionately ran for office on a bold promise he would ensure American supremacy over the USSR in space technology, a shining beacon of national pride. When he was successfully elected, he began looking at ways to keep this ambitious promise, and was initially quite shocked when he realized how much the whole endeavor would cost, a truly staggering sum. However, when the USSR completed yet another breathtaking space landmark on April 12, 1961, by getting the first human into space, cosmonaut Yuri Gagarin, President Kennedy's resolve hardened. This was no longer just about satellites. It was about human destiny, about who would lead the way into the future. He began to urgently ask his researchers what they could possibly do to match or even better exceed the Soviet progress to reclaim the leadership in this vital new frontier. The answer came back on April 20th of that same year, a bold, almost unbelievable proposition. If they wanted to truly beat the Soviet Union, who were already significantly ahead in the space race, thanks to their powerful R-7 rockets, they would need to aim for something that was currently outside of both nations' capabilities. They needed a goal so grand, so audacious, that it would inspire an entire nation and capture the imagination of the world. The target suggested was an internationally lofty one designed to impress the world, to leave no doubt as to American ingenuity and determination. NASA would put a man on the moon. This immense challenge would of course require unprecedented improvements to America's existing rocket technology. They would need to produce rockets 50 times as much force to lift all the rocketry and modules necessary to get a person to the moon and back, a colossal leap in power. NASA would also require a significantly higher budget and infusion of resources unlike anything seen before in a scientific endeavor. And indeed, this budget was swiftly approved. In 1961, NASA was given $744 million for their various projects, a substantial sum. Just a few years later, as the budgetary requirements ramped up with the sheer scale of the Apollo program, NASA was receiving over $5 billion per year, an astonishing investment that underscored the national commitment to this singular goal. NASA began using these colossal funds to rapidly expand their operations, building new launch sites and mission control centers, quiet nerve centers that would orchestrate humanity's journey to another world. They hired new staff, drawing in the brightest minds and most skilled hands from across the nation, forming a dedicated army of engineers, scientists, and technicians. They purchased vast quantities of research and development equipment, such as colossal vacuum chambers capable of nearly simulating the perfect vacuum of space, allowing them to test their equipment in conditions mimicking the silent void. NASA had already been quietly considering how to get a man to the moon in early 1960, even before Kennedy's bold declaration. But with this infusion of resources and profound political impetus, they began to consider the problem much more seriously, transforming a distant dream into a meticulously planned reality. There were various plans drawn up to explain how to go about getting a person on the moon, each a complex tapestry of engineering and logistics. Should they build one giant rocket that would fly straight to the moon and back again in a plan called direct ascent? Or maybe a more intricate dance, an Earth orbit rendezvous, might be a better option, where over the course of up to 15 separate rocket launches, various spacecraft parts could be carried up to and assembled in space like a giant cosmic puzzle. Each plan had its own compelling advantages and its own daunting difficulties, a quiet weighing of immense engineering challenges. Firstly, the idea of a single rocket flying straight to the moon and back again. The direct ascent plan presented immense hurdles. Such a rocket would be extraordinarily heavy and would require an incredible amount of lift or raw power, far beyond anything currently conceived. It would have to carry enough fuel to not only exit Earth's powerful gravitational pull, but also to escape the moon's gentle embrace and then return. This much extra weight was even further beyond the USA's existing rocket capabilities, a quiet acknowledgement of technological limitations. The second idea, the Earth orbit rendezvous to build a rocket in space, was problematic too, though in different ways. It would elegantly circumvent the initial lift issue, as carrying only a part of a spacecraft would be much lighter for each individual rocket. But launching so many rockets, up to 15 separate launches, would massively increase the overall costs and complexity of the project, a logistical nightmare. Each rocket launch, after all, would cost hundreds of millions of dollars, a truly staggering sum. And assembling a spacecraft in space in the vacuum and microgravity would be no easy feat, either requiring complex robotic arms or daring spacewalks of unprecedented duration. Finally, after much deliberation, after countless hours of quiet debate and meticulous calculation, NASA decided on a plan that they believed could use the best elements of both approaches. Their idea was to create a rocket that would gracefully come apart, shedding its components as needed, with a mission plan they called the Lunar Orbit Rendezvous LOR. This approach, which had quietly gained favor thanks to its efficiency and reduced complexity compared to other options, would involve a single colossal rocket taking two main modules out of Earth's orbit. These two modules were the Command Module CM, a capsule designed to carry the astronauts for most of the journey and serve as their living quarters, and another segment called the Lunar Module LM, a smaller, delicate craft specifically designed for the moon landing. These two modules would travel together to the moon, intertwined yet distinct. Once they reached lunar orbit, the lunar module, much smaller and lighter than the overall rocket, would gently detach from the command module and would take two of the astronauts down to the moon's surface. After their historic exploration, after collecting their precious samples and conducting their quiet experiments, it would then take them back up again, a delicate ascent from the lunar dust, to rendezvous and redock with the command module, which would have been patiently orbiting above. Once all the astronauts and their samples were safely transferred back to the command module, the lunar module, having fulfilled its purpose, would be jettisoned, left to quietly drift or crash onto the lunar surface. The command module, now carrying all three astronauts, would then travel alone, a solitary vessel, back to Earth, before finally splashing down in the ocean, a triumphant return to their home planet. This plan, though it sounds a little complex in its intricate choreography, was hoped to be the most economical model, both in terms of cost and, crucially, in terms of weight and thrust requirements. It allowed for a smaller total payload to be launched from Earth compared to the direct ascent, and avoided the immense complexities and costs of assembling a full spacecraft in Earth orbit. With this plan firmly in place, NASA could begin the monumental task of construction and testing. They would need to create rockets that were significantly larger and more powerful than anything they had ever done before, colossal machines that would literally shake the ground as they lifted humanity's hopes towards the heavens. They would need to put their own astronauts into space to test their mettle and their courage, and to thoroughly test each stage of the journey piece by painstaking piece to ensure the success of the program. But now, with a clear vision and an unprecedented infusion of resources, they were underway. The Apollo program, humanity's quiet, audacious quest for the moon, had truly begun. Humanity, in its boundless curiosity, sometimes finds moments of profound wonder in the most unexpected corners, even amidst the most serious of endeavors. There is something delightfully charming, perhaps even deeply human, in the quiet mischief that can bubble to the surface even on a mission as utterly momentous as the moon landing. Such was the case with the Apollo 14 astronauts who, with a twinkle in their eyes and a touch of playful daring, smuggled the head of a 6-iron, a golf club, to the moon. It was tucked away in one of their utility pockets, a secret piece of earthly leisure carried to an alien landscape, all to have a quick informal game of golf. This whimsical act broadcast, live across the silent vacuum of space, brought much amusement to the millions of TV viewers watching the moon landing live in their homes, a gentle moment of shared joy amidst the grand scientific undertaking. The Guinness World Record for the longest golf drive on Earth stands at an astonishing 5 and 15 yards, a mighty blow hit by Mike Austin. Unofficially, the longest drive in a professional golf tournament goes to K.L. Cooper at an incredible 787 yards, whose shot hit a downward running concrete path and took off taking lots of fortuitous bounces before finally coming to a rest. But let's quietly turn our attention to what might just be the longest golf drive, perhaps ever a shot struck on an entirely different world, by a man whose name is already etched in the annals of space history, Alan Shepard. Coincidentally, he also holds the distinction of being the first American in space. Imagine the scene: a man in a bulky, restrictive spacesuit, standing on the dusty, desolate lunar surface with the vast, silent blackness of space above and the pale blue marble of Earth hanging in the distance. He retrieves his makeshift club. You can hear his voice calm, and even as he explains to the millions listening back home. And while you're looking that up, you might recognize what I have in my hand. It's the handle for the contingency sample return. It just so happens to have a genuine 6-iron on the bottom of it. In my left hand, I have a little white pellet. He drops the small golf ball. Unfortunately, the suit is so stiff I can't do this with 2 hands. But I could try a little sand trap shot here. We've got more dirt than more dirt here. Here we go again. It looked like a slice to me. Laughter echoes from Mission Control. He hits again. There we go, 3. A pause. Time for one more. Another swing. Miles and miles and miles, he exclaims, his voice imbued with a sense of playful triumph. Alan Shepard takes 4 shots in all. The first shot doesn't have such a good connection, and instead kicks up a lot of rubble, a puff of lunar dust. The second shot is a slice the ball rolling a few feet away from him, a minor frustration, even on the moon. He retrieves the ball and hits it again. It goes a little bit further, but still not very far, a quiet testament to the difficulty of the task in such a cumbersome suit. He then drops his third and final ball, a white speck against the gray regolith. This time, with a final determined swing, he makes a good connection, sending it, as he so famously claimed, miles and miles. Chances are it didn't literally go miles, but estimates based on the physics of the moon's low gravity and the complete absence of an atmosphere have suggested that a good connection with the ball would indeed have sent it an astonishing 1 mile or 1,760 yards. Had he been wearing a more mobile spacesuit, one that allowed for a proper, powerful double-handed swing, the ball would have likely been able to achieve over 2 miles, a truly cosmic drive. And that's not all the Apollo 14 crew did to leave their unique mark. Edgar Mitchell, the other astronaut on the surface, with a similar spirit of gentle playfulness, threw a makeshift javelin. Upon reaching the lunar module, a silent angular resting place on the lunar plains, they even took a photo of the small crater that the javelin and one of the golf balls landed in, a charming record of their unique lunar recreation. To me, I think it's good to see a bit of childlike curiosity, a touch of everyday humanity, even on super serious missions like the moon landings. It reminds us that even amidst the gravitas of scientific exploration, there is still room for joy, for wonder, and for a touch of lighthearted mischief. So, there you have it. The unofficial longest golf drive ever happened, not on some manicured green, but on the silent, desolate landscape of the moon, a quiet testament to the enduring human spirit of play. From the playful swings of a golf club on the moon, let us now gently transition to another remarkable figure in space exploration, one whose quiet bravery often goes unsung, Ham the chimpanzee. He was in his own gentle way very special. He was the first hominid in space, a tiny, unwitting trailblazer whose journey set a crucial course for years of human space exploration to follow. So, what was his story, this quiet pioneer with curious eyes? Did he survive the pioneering journey, a voyage that took him further from Earth than anyone had ever gone before? I'm Alex Mullen, and you're watching Astrum, and together, we will recount the story of Ham the chimp and the profound legacy his mission left behind. Project Mercury, as we've explored, came about as a direct result of the intense, silent competition of the space race between the USSR and the USA. Both countries were furiously trying to be the first ones in space, not just for scientific advancement, but because it would be a powerful display of their military powers against the rival nation. This fierce, quiet competition was the very context from which NASA and Project Mercury itself was founded. Before Project Mercury in the early 1950s, space-related endeavors were largely performed by the U.S. military, their focus more on the mechanics of flight than on life itself. Initially, they sent mice and monkeys into space, tiny unwilling passengers in rockets, to gently test the unknown effects of huge G-forces and the strange sensation of weightlessness that comes with rocket travel. The rockets themselves were very basic, to begin with simple metal tubes pointing towards the sky. This particular rocket, called the Aerobee B3, is pretty small by today's towering standards, at only 8 meters tall. In this specific test, it reached altitudes of only 60 kilometers, a brief kiss of the upper atmosphere, experiencing a maximum of 4 Gs on takeoff and weightlessness for a few exhilarating minutes. The animals inside the rocket, observed through various instruments, appeared perplexed, perhaps a little disoriented, but crucially, they survived the trip with no apparent harm or aftereffects. A quiet sigh of relief for the scientists. Monkeys were specifically chosen during this time because they closely matched the physiology of humans, a gentle echo of our own biological makeup. It was thought, with a hopeful logic, that whatever happened to them would be a good indicator of what would happen to a human in space. Their reactions, their survival, were vital clues. One of the last space missions of the U.S. military before NASA took over was in 1959, where they successfully launched 2 monkeys, Miss Able and Miss Baker, into space. They soared to an altitude of 570 kilometers on board a Jupiter rocket. On this journey, they bravely withstood a maximum of 38 Gs, a crushing force that would render a human unconscious, and reached a top speed of 16,000 kilometers per hour, a breathtaking velocity. The mission was, in many ways, a profound success. The nose cone was successfully recovered, bringing the tiny pioneers safely back to Earth. But unfortunately, Miss Able, after enduring so much tragically, died a few days after the flight, after having surgery performed on her unsuccessfully, a somber reminder of the fragility of life and the risks involved. Miss Baker, on the other hand, a resilient little survivor, lived a while after the flight and was even able to breed as part of tests on her reproductive organs, providing further invaluable scientific data. She was honored for her contributions to scientific discovery, and even today bananas can be found on her grave. A quiet, sweet tribute in respect to her accomplishments, a symbol of our lasting gratitude. A few months after this pivotal flight, NASA, now formally established with Project Mercury at its heart, took over the monumental goal of bringing humans to space. They were armed with a new set of rockets, including the Mercury Atlas and the Mercury Redstone powerful machines, designed for a new era of exploration. America was under intense pressure. A quiet sense of urgency by the Russians, who had already achieved the groundbreaking feat of being the first ones to get a satellite into orbit in 1957, the famous Sputnik 1, and its haunting, persistent, beeping radio transmission. After a couple of years of rigorous testing, the Mercury rockets in 1961, NASA felt with a cautious optimism that they were ready to send a hominid, a great ape, into space aboard a Mercury Redstone rocket. This rocket was considerably bigger than the Aero B at 25 meters long, a much more formidable machine, but still much smaller than the towering giants of today. It was, however, large enough to fit a human in the capsule at the top, a silent promise of future human voyages. The Mercury Redstone rocket was only capable of suborbital flight, though meaning it would reach space, experience weightlessness, but not be able to stay in sustained orbit. Its journey was a powerful arc up and then back down. The choice of candidate for this profoundly important mission was, of course, critical. In this particular case, the chimpanzee would not just be a passenger, a passive observer of the journey, but would be explicitly required to perform tasks while in space. This was a crucial test. Could a living being under the stress and strangeness of spaceflight still follow commands and execute specific actions? The ability to perform tasks while in the capsule would pave the way for human astronauts in the future, meaning that human astronauts would not have to totally rely on automation, a fragile dependency should the rocket lose contact with the command base for whatever reason. From a pool of 40 chimpanzee candidates, each one carefully observed and evaluated, Ham was eventually chosen. His selection was the result of a rigorous series of processes, including selecting the healthiest chimp, and crucially the one that followed commands best. He was also picked because he was a particularly happy chimp with a good temperament, a gentle cooperative spirit that would ideally withstand the rigors of the journey. At this point, Ham was only known as Number 65, a cautious anonymity as the U.S. didn't want the potential negative press associated with a named chimp dying. Should the mission fail, a pragmatic approach to public perception, Ham was painstakingly trained to perform a simple yet critical task, to pull a lever within 5 seconds of seeing a blue light. If he did so correctly, he would be immediately rewarded with a banana pellet, a sweet reinforcement of the desired behavior. Should he not pull the lever, he would receive a mild electric shock in his foot, a gentle yet firm consequence designed to ensure compliance. After months of these meticulous preparations, Ham, in his own quiet way, was ready for the flight. They gently inserted him into a mini capsule, at first a custom-built environment that served as a kind of personal spacesuit for the chimp. This mini capsule was ingeniously designed to control pressure, oxygen, and temperature specifically for Ham, ensuring his comfort and safety. He had sensors meticulously attached, measuring his vital signs quietly, communicating this critical information back to ground control on Earth, thanks to the rocket's antenna, a constant stream of data. His arms were left free, a thoughtful design, in order to perform the commands he was given during the flight, allowing him to pull the crucial lever. And he had a small window, a tiny portal to the outside world, so he could see what was going on, a witness to his own incredible journey. The time for the launch approached, pregnant with quiet anticipation. Many scientists and engineers bustled around doing last-minute checks, their faces etched with concentration to ensure everything went perfectly with the flight. Ham was then gently placed into the main capsule of the Mercury Redstone rocket for launch. This main capsule was also pressurized, as this was where the human astronaut would sit should this mission go according to plan. As the morning arrived, crisp and expectant, the rocket finally launched a thunderous roar, shaking the very ground beneath their feet. However, almost immediately, a quiet, unsettling anomaly appeared. After only 1 minute into the flight, computers on board, the rocket communicated back to command that the flight plan angle was already 1 degree too high and rising, a subtle deviation that would have profound consequences. This steeper angle meant the rocket accelerated a lot faster than planned, pushing Ham's tiny body with predicted G-forces reaching 17 Gs in the capsule, a crushing force far more than anticipated. After just 2.5 minutes, the liquid oxygen for the rocket was prematurely depleted, a critical malfunction, which sent a mayday signal to recovery forces. The rocket, now an untethered giant, was spinning wildly, was a lot higher than expected, and had achieved higher speeds than anticipated. In a swift, desperate response to this alarming cascade of malfunctions, an abort signal was sent. and the capsule carrying its tiny unwitting passenger was ejected early from the rocket at an altitude of 250 kilometers instead of the planned 185. This earlier abort meant that there were no retro-rockets to slow the descent, no gentle brake. The capsule containing Ham, a fragile shell in the vastness, hurtled back towards Earth, a silent, accelerating projectile. If this wasn't enough, more alarming whispers came from the sensors. They reported that the main capsule was losing pressure fast, a life-threatening failure. This later turned out to be a faulty air inlet snorkel valve, a tiny, almost imperceptible pin, of which had come loose after the intense vibrations from the launch, a cascade of unforeseen errors. At this point, though, in his protected mini-capsule, Ham was blissfully unaware of all these terrifying problems going on around him. His personal mini-capsule meant that he was utterly unaffected by the rapidly falling pressure in the main capsule. He was with a quiet determination, happily playing the lever and lights game, performing his trained task, only marginally slower than his results on Earth. His small, brave mind was focused on the blue light and the promise of a banana pellet, even as the world around him outside his protective shell was in chaos. As the capsule began its fiery re-entry back into Earth's atmosphere, Ham was again subjected to higher G-forces than expected. This time 14 Gs, another crushing force, a testament to the uncontrolled descent. Because there were no retro-rockets fired to slow its fall, the capsule had overshot its expected landing area by a significant 100 kilometers. The capsule's parachutes, designed to gently slow its plunge, were pulled open, and airbags around the base were inflated to cushion the fall and help with floating on the water's surface upon impact. Color dye, a bright, hopeful splash against the dark ocean, was released into the sea to help aid recovery. It wasn't until 12 excruciating minutes had passed a lifetime of anxious waiting before the capsule finally sent its first recovery signal, a faint, precious whisper of survival. And then 27 minutes after landing, a search plane finally spotted the capsule, a tiny beacon of hope floating resiliently in the vast Atlantic. The U.S. Navy rescue helicopters were immediately sent from the nearest ship to pick up the capsule, which by the time they got there had taken in water and was quickly submerging a race against the inevitable. The impact from the landing had surprisingly popped off the heat shield at the base, puncturing holes into the base of the capsule. The airbags were heavily worn, their protective cushioning diminished, and that leaky snorkel valve from earlier was also allowing water in, turning the capsule into a slowly sinking vessel. By the time the capsule was rescued, it had taken in roughly 360 kilograms of water on board, a heavy burden for such a small craft. After a grueling 3-hour recovery, the capsule and its precious cargo were airlifted to the nearest Navy ship, where NASA scientists waited on hand, their faces etched with a mixture of anxiety and hope to see the fate of Ham. A lot had gone wrong with this mission, almost everything that could have. But was he still alive after all of that? And if so, what state was he in, this brave little pioneer? Scientists and Navy personnel worked quickly, their movements precise and urgent, to gently get him out. The cover came off, and there he was. Ham was fine. He had done it. He was safe and well, still his happy self, almost as if nothing noteworthy had happened, a testament to his resilient spirit and the robust design of his mini-capsule. He had survived everything relatively unscathed. His only injury, a tiny, almost endearing mark of his extraordinary journey, was a bruised nose. Ham retired from spacefaring shortly thereafter, his pioneering work complete, and lived a good 20 years after his voyage in a number of zoos, a quiet, peaceful life on Earth after his cosmic adventure. He passed away in 1983. His skeleton was sent to the U.S. National Museum of Health and Medicine, a scientific legacy, while his other remains were buried and honored by the International Space Hall of Fame in New Mexico, a fitting tribute to a true trailblazer. Because of the profound success of this mission, the quiet demonstration that a hominid could survive the rigors of spaceflight and perform tasks a few months later, the U.S. successfully sent Alan Shepard into space, aboard another Mercury Redstone rocket called Freedom 7. However, despite these crucial steps, the US didn't ultimately win this particular space race to put a human in orbit first. The Soviets, with their characteristic stealth and efficiency, had already successfully orbited around the Earth, with a human on board, Yuri Gagarin, aboard Vostok 1. But the quiet, profound legacy of Ham's mission can still be felt today, a gentle echo in the vastness of human endeavor. With humans now routinely on board the International Space Station, and even now with a new space race unfolding to get humans on the moon a second time. So there we have it, the remarkable tender story of the chimp who beat all humans to space. Ham, the silent pioneer whose brave journey laid a vital foundation for all who followed. In 1977, two pioneers, not of flesh and blood, but of intricate circuitry and gleaming metal, embarked on what might be one of the most epic feats of exploration ever undertaken. Their quiet goal to unravel the cosmic mysteries surrounding the solar system and our fragile place within it. These were the Voyager 1 and 2 probes launched into the silent embrace of space, each a tiny, intrepid messenger from Earth. Not only did they provide us with some of the very first and most breathtaking imagery of our solar system's outer planets, painting vivid portraits of worlds previously seen only as distant pinpricks of light, but they continue even now to send us incredible new information about our universe from the cold, deep reaches of interstellar space, some 47 years and an astonishing 24 billion kilometers later. The Voyager probes are more than just instruments and circuitry, more than mere collections of wires and sensors. They are a profound symbol of humanity at its very best, curious, audacious, ambitious, and resilient. Voyager didn't just capture dazzling photos of our gas giants and their moons. It captured the hearts and minds of generations back home on Earth, weaving a new thread into our collective understanding of the cosmos. As Edward Stone, the Voyager Mission Project scientist, so eloquently put it, "When I look back, I realize how little we actually knew about the solar system before Voyager. We discovered things we didn't know were there to be discovered time after time. It is a testament to the humbling power of true exploration, where the greatest discoveries are often the ones we never anticipated." I'm Alex Molin, and you're watching Astrum. Join me today as we trace Voyager's iconic journey in pictures, a silent visual symphony through our solar system. From the swirling splendor of Jupiter, to Saturn's icy intricate rings, to the topsy-turvy world of Uranus, and finally, to the mighty mysterious storms of Neptune, we will quietly explore what this monumental mission taught us about our planetary neighborhood, revealing its hidden wonders and deepening our sense of cosmic awe. The Grand Odyssey began on August 20th, 1977, when NASA launched the Voyager 2 space probe from Cape Canaveral, Florida, a gentle, powerful push into the unknown. Its partner in this cosmic crime, Voyager 1, followed just 2 weeks later on September 5th, a synchronized departure. Even though both probes were destined for Jupiter, their paths were subtly different. Voyager 1 was set on a shorter, faster trajectory designed to reach Jupiter sooner, which is why, despite launching second, it made sense for it to overtake Voyager 2 on December 15th of 1977, quietly pulling ahead and exiting the asteroid belt first. Together, this dynamic duo was set to take advantage of an extraordinarily rare celestial alignment, a once-in-a-176-year planetary configuration. Jupiter, Saturn, Uranus, and Neptune were going to be aligned in a way that would allow one mission to explore all four gas giants through a series of gravitational assists, a cosmic slingshot effect. It was an opportunity NASA simply refused to miss, a whispered invitation from the cosmos itself. After some back and forth with the U.S. Congress, a few hurdles surrounding budget approvals, and a decade of painstaking, quiet, hard work, the Voyager probes finally made it to the launch pad, heralding a new, breathtaking era of space exploration. The dazzling parade of pictures Voyager would send back were absolutely revolutionary at the time, transforming blurry dots of light into vibrant, complex worlds. But don't take my word for it. Let's gently jump in, and you'll see for yourself. Just 13 days after launch, Voyager 1 sent this photo back to Earth, the very first of tens of thousands it would transmit over the next 5 years. Taken 11.6 million kilometers from Earth, it's a sentimental, almost haunting place to start our journey. It might gently remind you of the iconic Earthrise photo taken by the Apollo 8 crew from the Moon. Just 8 years prior, a poignant reminder of our fragile home. Here we can see our blue marble and its small loyal moon. In the vast distance, a tiny island of life in an ocean of black. I don't know about you, but I find this photo so hauntingly beautiful, especially knowing how far this tiny probe traveled and how much it's seen since then, a silent witness to cosmic wonders. But we've got a long way to go, so let's quietly move on. It would be almost 2 years before Voyager 1 finally made its approach into its first majestic target, Jupiter. Imagine that a journey across 714 million kilometers, a vast, silent expanse. Voyager 1 arrived first on March 5, 1979. You see, it travels at 17 kilometers per second, 2 kilometers per second faster than Voyager 2, who, despite leaving Earth first, arrived 4 months later, on July 9, 1979. This is because the trajectory Voyager 1 took allowed it to gain more speed relative to the Sun, a subtle yet crucial difference in its cosmic path. Now, Voyager 1 was not the very first spacecraft to encounter Jupiter. That honor belonged to Pioneer 10, 7 years prior in 1972. And while the Pioneer mission certainly provided great scientific insights, it didn't quite grab the imagination of the public in the same profound way. But sending back stunning images like this Voyager certainly did. This is Jupiter in all its glory, a swirling masterpiece of color and motion. It's kind of hard to accept that these are actual photos and not some magnificent painting or an AI-generated image. If you look closely, you can spot 2 of its loyal moons, Io on the left and Europa, the beige one, on the right, each a tiny companion to the gas giant, but more on them later. Luckily for us, Voyager 1 even quietly recorded its approach to the great gas giant. It took photos at regular intervals every 10 hours, which is exactly 1 Jupiter day. This means the planet is in the same point of its rotation in all the photos, allowing for a seamless, mesmerizing progression. The 66 photos were spliced together to create this time-lapse movie spanning Voyager 1's approach to Jupiter from January 6th to February 3rd, 1979, covering a colossal distance of 27 million kilometers. I personally can't decide if it is incredibly breathtaking or subtly terrifying, this relentless swirling giant. But let's get a closer look and see what quiet surprises this planet is hiding within its turbulent embrace. Something that immediately stunned scientists. Something they had not fully anticipated was the sheer dynamism of Jupiter's atmosphere. They had expected to see broad, organized east-west and west-east winds in Jupiter's different atmospheric zones, a predictable pattern. But what caught them by profound surprise was the astonishing amount of turbulence, plumes, and rotational movement, which are super clear in this image. You can immediately see how profoundly dynamic and alive the atmosphere of Jupiter truly is, a swirling cauldron of energy. Scientists had already suspected Jupiter's most notable characteristic. Its iconic Great Red Spot might be a counterclockwise rotating formation, a colossal persistent storm that had raged for centuries. Not only did Voyager data confirm this, but it also showed a surprising amount of similar phenomena in other parts of the atmosphere. The white spot you see below the Great Red Spot is just one gentle example of these surprise storms, smaller yet equally dynamic. It turns out Jupiter's atmosphere is literally littered with them, a chaotic symphony of weather systems, and before Voyager, we had almost no idea of their intricate dance. When we think of rings, our minds instantly conjure images of Saturn, its iconic ethereal halo. But thanks to earlier Pioneer data scientists had long suspected that the same might be true for Jupiter, a whispered possibility. Voyager data not only definitively confirmed the existence of 4 Jovian rings, thin, delicate strands of cosmic dust. But it was also the very first mission to capture their images, painting them into existence for human eyes. This particular picture taken as Voyager leaves Jupiter's gravitational embrace, highlights the rings beautifully appearing as that glowing orange line subtly protruding from the planet's limb, a silent, newly discovered feature. Before we gently leave Jupiter and continue our grand journey, I did promise we would come back to its moons, Io and Europa, two companions, holding unexpected secrets. Possibly the biggest shock, the most breathtaking revelation from the Voyager expedition, was the astonishing discovery of volcanic activity on Jupiter's moon Io. Prior to Voyager geologists, with their earthly understanding, thought Io would be covered with large impact craters, much like our own serene moon, a pockmarked landscape of ancient history. While they did find circular markings on Io's surface, they immediately noticed that these did not appear to be from craters, but something far more active, far more violent. The dark spots you see are not shadows, but telltale indicators of the presence of volcanic hotspots and lava lakes, glowing furnaces on a distant moon. This photo clearly shows lava flow from less than 1 million years ago, which is incredibly recent in geological terms and totally, utterly unexpected. We now know Io as the most geologically active site in the entire solar system, a fiery crucible in constant turmoil. At the time of these images being taken, it would have been truly incredible to capture Io mid-eruption, a volcanic plume soaring into the vacuum. Imagine expecting to see a quiet, dead moon, similar to ours, then stumbling upon a sight like this. These brilliant blue explosions on the surface of Io, captured by Voyager's patient gaze, shot material and gas, an astonishing 100 kilometers into space, a silent, powerful display. The volcanoes are incredibly active, going off relentlessly every few hours, treating Voyager to several jaw-dropping photos, each one a new revelation. The next moon out from Io is Europa, and it could not be more different, a stark, beautiful contrast. Europa is an icy world, shrouded in a gleaming shell of frozen water. Voyager 1 was the very first probe to show us that Europa is covered by curious scratch markings, intricate patterns etched across its surface. Scientists puzzling over these strange features supposed them to be some type of ice fracture patterns on Europa's surface cracks in its frozen skin. It was also Voyager data that first subtly suggested there might be a swirling ocean, a vast sea of liquid water lurking under the thick ice, a profound hint of potential life beneath the frigid surface. Today, we know of an astounding 95 moons orbiting Jupiter, a vast cosmic family. However, prior to 1979, that number was a mere 13. Voyager quietly, yet significantly discovered 3 new satellites, Metis and Adrastea, bringing the total to 16 moons by the early 80s, a quiet expansion of our known solar system. Sadly, we don't have any actual pictures of them from 1979 that are widely published, though they have been imaged extensively since then. The next majestic stop on Voyager's grand tour was Saturn, the ringed jewel of our solar system. After 21 months of silent, relentless travel, Voyager 1 arrived on approach to the ring planet in November 1980, closely followed by its companion Voyager 2 9 months later in August 1981. Like I said before, when you think of rings, your mind instantly thinks of Saturn, its iconic ethereal embrace. So, let's start there, exploring the silent beauty of its halo. Prior to Voyager's mission, Saturn was believed to have just 5 major rings, broad distinct bands circling the planet. However, Voyager 1, with its incredibly sharp vision, showed us that these rings are actually made up of hundreds of thin ringlets, countless delicate strands like a cosmic tapestry woven from icy dust. This was the closest flyby any probe had undertaken back then, hence the incredible detail and profound learnings it provided. Voyager also quietly discovered a new ring, the G ring, a faint, almost invisible band, and provided crucial intricate details about the E ring, which had been partially discovered by Pioneer 2 1 year prior in 1979. Voyager 1 showed us that the E-ring is kinked and multi-stranded in nature, a complex braided structure. It also identified 2 fascinating small moons, the shepherd moons, Prometheus and Pandora, orbiting within the E-ring, acting as gravitational guardians, gently corralling the ring material and keeping it in line. This was big news, because this discovery definitively confirmed scientists' theories that shepherd moons exist around narrow rings to keep ring material in line, a beautiful demonstration of gravitational ballet. Voyager also introduced us to some ghostly features on Saturn's B-rings features that appeared scattered around the rings in this photo and are said to resemble broad spokes in a wheel. They seem innocent, almost ethereal, but they actually caused quite the stir, a quiet scientific puzzle in the scientific community for a while. You see, up until 1980, we thought that Saturn's rings were caused exclusively by gravitational forces, that their structure was solely dictated by the elegant pull of celestial mechanics. That's all well and good, except these spokes completely fly in the face of that theory. Their very existence is not consistent with conventional gravitational orbital mechanics. We still don't definitively know what causes them, a lingering mystery. But the leading theory involves electrostatic repulsion, subtly separating very small dust particles from the main surface of the ring, a gentle unseen force at play. Sadly, as much as data from Voyager taught us about Saturn's rings, it also taught us a quiet, poignant truth. Saturn is slowly, steadily losing its rings. Gravity, with its relentless gentle pull, is drawing the rings into the planet, turning them into a kind of dusty rain of ice particles, a slow, beautiful dissolution. According to current estimates, this could cause Saturn's rings to completely disappear in about 300 million years, a mere blink in cosmic time. Voyager's quiet, profound trip to Saturn raised so many new questions, opened so many new avenues of inquiry, that a dedicated mission was later mounted, a subsequent journey exclusively to study the ringed planet. This was the Cassini probe, which launched in 1997 and meticulously orbited Saturn for 13 years, providing an unprecedented wealth of data. But we aren't leaving Saturn territory just yet. Voyager provided some decisive breakthroughs regarding the planet's moons. We already knew of 14 moons, a modest family, but Voyager, with its keen eyes, showed us 3 more, bringing the total number at the time up to 17 moons, a silent expansion of our celestial neighborhood. Let's see what we can learn from Titan and Enceladus, 2 of Saturn's most intriguing companions. Pioneer 11 was the first probe to image Titan, Saturn's largest moon, a world shrouded in mystery. And the data it gathered subtly captured the interest of researchers, hinting at something unique. So Voyager was sent to follow up, to peel back the layers of its atmospheric veil. It found that Titan had a thick, nitrogen-rich atmosphere, the first and only encounter of such an atmosphere beyond our home planet. Imagine that, a distant moon, with an atmosphere strikingly similar in composition to Earth's, a silent echo across billions of miles. Enceladus also turned out to be exceptionally quirky, a tiny, fascinating world of wonders. Take a look at this photo. Enceladus is visible out in the distance, a small icy orb, with Saturn majestic and ringed in the foreground. Now, I know it's tricky to see, but that moon is literally erupting. Enceladus spews out an astonishing 300 kilograms of water vapor, up to 10,000 kilometers above its surface, 20 times its own diameter, as it gracefully orbits Saturn, a continuous quiet geyser in space. The frequent plumes of water vapor that erupt leave a donut-shaped cloud, a subtle ethereal ring that gently feeds one of Saturn's icy rings, a beautiful, unexpected connection. This data was initially suggested by Voyager data, but it wasn't until we flew Cassini out there decades later that we could definitively confirm it to be true, a testament to the power of follow-up missions. Further geological data and imaging shows that Enceladus's terrains are an unexpected mixture of old and new. The left side, which appears smooth, is the newest side, a fresh canvas, and the right side, with its densely packed impact craters, is the older side, bearing the scars of cosmic history. This suggests Enceladus is a very geologically active moon, far more than it was previously thought to be a small icy world alive with internal forces. Before we make our way to the wonky, enigmatic world of Uranus, we must gently say goodbye to Voyager 1. After its magnificent flyby of Titan and Saturn's breathtaking rings, its path was subtly bent upward out of the ecliptic plane, the relatively flat disk, where most of the planets orbit the Sun. From here, the probe headed straight for the grand silent expanse of interstellar space, a journey into the true cosmic ocean. Of course, it would be another 32 years of patient, tireless voyage before it would finally reach that boundless realm, but its course was set. But not to worry for its steadfast companion. Voyager 2 took a slightly different path, performing a graceful slingshot around Saturn, instead using the giant planet's gravity to propel it onward to the distant unseen worlds of Uranus and Neptune. These would be truly pioneering encounters, the first and only flybys of these planets in human history, a unique moment of cosmic revelation. 5 quiet years after arriving at Saturn, NASA's Voyager 2 arrived on approach to Uranus in January 1986. At its closest, the probe came within an astonishing 81,500 kilometers of Uranus's swirling cloud tops, a breathtakingly close encounter with a world shrouded in mystery. Voyager 2, with its keen vision, revealed something unexpected and profoundly serene, an absence of visible cloud features in Uranus's atmosphere. Unlike the dynamic turbulent atmospheres of Jupiter and Saturn, Uranus displayed a remarkably serene, almost featureless cloud deck, a puzzling tranquility that challenged scientists' preconceptions about the atmospheric dynamics of gas giants. The false color image on the right helps to gently bring out the subtle differences in the atmosphere of the polar regions, which are themselves tilted on a peculiar 98-degree axis, a world spinning on its side. But it was another tilt that utterly stunned the Voyager scientists. It was previously unknown whether Uranus even possessed a magnetic field, a fundamental planetary characteristic. But Voyager data, with its precise measurements, showed us that not only does Uranus indeed have a magnetic field, but it is also tilted at an astonishing 59 degrees relative to its rotational axis. Imagine that its magnetic and rotational poles are not at all in the same place. Until then, it was quietly assumed that these poles were always aligned as they are here on Earth, where our magnetic and rotational poles are only shifted by a mere 12 degrees. The stark dramatic deviation found on Uranus defied conventional planetary magnetic field models and forced scientists to rethink their fundamental assumptions about how planetary dynamos work, a quiet revolution in our understanding. One fascinating side effect of this profound misalignment of poles is that as the planet spins its magnetosphere, the vast invisible space carved out by its magnetic field wobbles wildly like a poorly thrown football tumbling through the cosmic air. Scientists still don't quite know how to fully model it, a lingering mystery, but it might look something like this in the quiet depths of space. Voyager 2's observations also unveiled more intricate details about the known rings of Uranus, and with a quiet triumph, discovered 2 more. It was the first mission to capture clear images of these dark, delicate rings, like its outermost rings, barely visible in this photo. These newly discovered rings are composed of fine dust particles, ethereal strands woven around the planet. Voyager 2 also quietly discovered 2 more shepherd moons orbiting one of the newly discovered rings, similar to its profound findings with Saturn's F ring. Here, they can be seen from 4 million kilometers in a photo from January 21st, 1986, tiny gravitational shepherds guiding their dusty flocks. This mission profoundly increased the known count of Uranian moons. Prior to Voyager 2, we only knew about 5 moons orbiting Uranus. Voyager 2 sent us the first ever images of these moons, which you'll see in a moment. But it also astonishingly discovered 11 more moons, bringing the total to 16 moons, a silent explosion of new worlds. Voyager's discoveries provided invaluable data on these new moons' sizes, composition, and orbital characteristics, painting a richer portrait of this distant system. Today, the number of known moons of Uranus stands at 27, a testament to continued observation and discovery. Okay, back to Uranus's 5 original moons, those silent companions observed from Earth. They all appear to be ice rock conglomerates, a mixture of frozen water and silicate rock, similar in composition to many of the moons of Saturn. Oberon and Umbriel, pictured here on January 24, 1986, are riddled with impact craters bearing the scars of billions of years of cosmic bombardment. They seem to have little geological activity, judging by their old and dark surfaces, quiet, unchanging worlds. Titania, which sits between those two. The fourth furthest from Uranus is marked by huge fault systems and canyons, suggesting some degree of past geological and probably tectonic activity in its history, a world that was once restless. Ariel has the brightest and possibly youngest surface of all the Uranian moons. This photo, taken from just 129,000 kilometers, suggests Ariel underwent significant geological activity that led to many fault valleys and extensive flows of icy material. At some point in its history, a testament to a dynamic frozen past. But the closest of the 5 original moons to the planet, second only in proximity to Puck, the little rocky satellite discovered by Voyager in 1985, was Miranda. And Miranda, tiny and unassuming, held the most surprising findings of all. Voyager flew by Miranda on January 24, 1986, at a remarkable distance of just 30,000 kilometers, an incredibly close encounter. This small moon, far from being a simple dead rock, turned out to be a captivating puzzle of geological dynamism, shaped by a volatile, almost violent history. Voyager 2 identified traces of internal melting and sporadic upwelling of icy material, manifesting in extensive canyon-like faults, plunging to astonishing depths of up to 20 kilometers far deeper than any canyon on Earth. The lunar canvas is further adorned with oval racetrack-shaped features, quietly etched like cosmic scratches. Voyager also saw terraced regions where a mosaic of old and young, bright and dark and heavily and lightly cratered terrains coexist, a geological jumble. The chevron-like characteristic seen here suggests Miranda's original surface was somehow pulled apart and the fragments forcibly reaggregated back together, a cosmic jigsaw puzzle violently rearranged. 3 weeks later, on January 25, 1986, Voyager 2 gracefully departed Uranus and snapped this wonderful goodbye shot from 1 million kilometers as it set off to its final planetary target, Neptune. After 3 more years of silent, relentless travel, a journey across billions of kilometers at a speed of 54,000 kilometers per hour, Neptune finally came into view. Voyager 2 approached the furthest planet in our solar system on August 25, 1989, just over 12 years since it took off from Earth. It produced the first close-up images we've ever received of the giant blue planet passing only 5,000 kilometers above its north pole, the closest of any planetary flybys in the mission. Hydrogen was found to be the most common element in Neptune's atmosphere, forming the vast bulk of its gaseous embrace, although the high abundance of methane is what gives the planet its striking blue appearance. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere, a truly fierce display with the equatorial winds blowing at speeds reaching almost 100 kilometers per hour. These remarkable speeds were yet another profound surprise, highlighting just how dynamic and ferocious Neptune's weather systems are. Scientists also discovered a massive storm on Neptune, aptly named the Great Dark Spot, a powerful ephemeral eye gazing into the void. This turbulent storm seemed to be rotating counterclockwise, just like the Great Red Spot on Jupiter, and exhibited winds reaching up to an incredible 2,400 kilometers per hour the strongest recorded in the entire solar system. One NASA analyst, Ken Ballinger, commented on the findings in 1989, saying, "Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling." This change is going on constantly on Neptune that happened very, very fast. A testament to the ever-unfolding wonders of the cosmos, Voyager 2 also imaged Neptune's rings for the first time. Up until 1986, scientists suspected the planet might have rings, but couldn't be certain. Intriguingly, the spacecraft identified several partial ring structures, or ring arcs, within Neptune's ring system. These arcs raised fascinating questions about the mechanisms responsible for their formation and stability, as they mainly consist of incomplete and dusty rings, a delicate fragmented halo. A trip to Neptune wouldn't be complete without a quick stop over at its largest moon, Triton. Triton, the coldest known planetary body in the solar system, a world of deep, profound chill, turned out to have a fractured surface complete with erupting geysers of nitrogen ice and a pinkish nitrogen ice cap over its southern pole, a striking alien landscape. Scientists also identified dark plumes, which could indicate the possibility of ice volcanoes, a silent, frigid version of Io's fiery dance. Voyager 2 also quietly discovered 6 new moons orbiting Neptune, including these tiny, previously unseen companions, as Voyager 2 gently turned around to snap one last poignant look at Neptune and Triton. Its primary mission was officially complete. It had successfully completed its grand tour, a journey spanning the entire outer solar system. Neptune's immense gravity bent its path downward out of the ecliptic plane, sending it on a new trajectory. From here, it continued its magnificent voyage into interstellar space, just like its counterpart Voyager 1 had done 9 years before. Speaking of Voyager 1, let's gently see where it's ended up since we last checked in. In 1980, a year after Voyager 2 finished up with Neptune, Voyager 1 was already about 6 billion kilometers away, a truly immense distance. In order to conserve precious power for the unimaginably long journey into interstellar space, scientists were going to switch off its cameras forever, a quiet, necessary act of preservation. However, on the wise advice of Carl Sagan, whose poetic vision illuminated the cosmos for so many, the team decided to turn the camera around for one final profound picture. A look back at home, a tiny blue marble, and a reflection on how far we had come. And so, on February 14, 1990, Voyager 1 took the most remote selfie in history from an astonishing 6 billion kilometers away. The result? The infamous deeply moving pale blue dot photo. In the immortal resonant words of Carl Sagan himself, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard, of every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." This profound sentiment rings with as much power today as it did 33 years ago, a timeless meditation on our fragile, precious existence. Both Voyagers 1 and 2 are still operational today, their faint signals whispering across billions of miles. Though Voyager 1 is experiencing a bit of a technical glitch at the moment, a tiny wrinkle in its long journey. Still, it is an incredible feat that we've managed to get both probes into interstellar space further than any other man-made device. Provided this glitch can be fixed, these intrepid probes are estimated to remain viable for a few more years before finally running out of power and going dark forever, their silent mission complete. While we aren't certain what these pioneering probes will encounter in the mysterious depths of space, we can be sure that the incredible images they provided back home have inspired generations of scientists, engineers, stargazers, and dreamers. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our profound responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Thanks for joining me on this journey. I was honestly blown away by all the incredibly kind comments and messages you sent me, and by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term patron member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.